Chapter 6, more on future value and present value. In the previous chapter, chapter 5, what we were doing was working with a single cash flow. We would be interested in finding its future value or its present value, and also some other additional things like the number of years or the interest rate. In chapter 6, we are going to be doing essentially exactly the same calculations, finding the future value, the present value, as well as the dollar amount of the cash flow and the interest rate, except we will be working with many cash flows. And then later in the chapter, we will introduce special cases in which cash flows are identical rather than different values. Let's start with this example. You deposit $500 in a bank today and $600 in 1 year into the same bank account. The bank pays a 9% interest annually to its depositors. Question: how much will you have in 2 years in your bank account? What's going on here is that we no longer have a single cash flow for which we need to find the future value. We have two cash flows. We have $500 deposited now and $600 deposited in 1 year. And we need to find their combined future value 2 years from today. The way we would solve something like this is break it into individual cash flows. First, find the future value of the first cash flow, $500 deposited now. What will its future value be after 2 years? If you use the formula for future value from chapter 5, you would do 500 multiplied by open parenthesis 1 plus 0.09 close parenthesis raised to the second power. That would give you $594.05. And you can also do it in the financial calculator if you use 500, set it to negative, save as PV, then 9 for IY, 2 for N, and compute FV. Then separately you will do a similar thing for your second cash flow, $600 deposited in 1 year. What is its future value? First, notice that we can no longer use the future value after 2 years, like we did for $500 deposited today. We have to use 1 year for the correct number of time periods. That's because the number of time periods, what it really means is over how many years your money will be earning interest and growing. For $600, there's only 1 year for that. And so using the formula for future value, we would do 600 multiplied by open parenthesis 1 plus 0.09 close parenthesis, which would give us $654. Or in the financial calculator, in no particular order, you enter the present value, the interest rate, and the number of years. For example, you can do 600, change it to negative, PV, then 9 IY, then 1 N, and then compute FV. Once you've done future values for your individual cash flows, then you simply combine them. You find the total future value. You combine $594.05 and $654. And the answer to this problem is, at the end of 2 years, you will have a total of $1,248.05. That's from 2 deposits made at different points of time. To summarize, in the financial calculator or using the future value formula, you find individual future values, one cash flow at a time, and then you add up the individual future values. Unfortunately, you cannot solve something like this in one step. Example: you're offered an investment that will pay you $200 at the end of the first year, $400 at the end of the second year, $600 at the end of the third year, and $800 at the end of the fourth year. You can earn a 12% return on similar investments. What is the most you should pay for this investment today? How do you approach problems like this? Essentially, it's implying that you should not want to invest more than what you're getting back in the future, right? We will be getting back 4 different dollar amounts in the future over 4 different years. The wrong thing to do is to simply add up 200, 400, 600, and 800. In finance, kind of one of the basic rules you learn over time, which is not even written in the books, is that you can never add things up that occur at different points of time. You need to sort of, add up apples rather than apples and oranges and so on. So how do we make them in a way that we can correctly add them up? We need to, for example, bring them all to year 0. Discount back to today. And that's really what the question is asking us to do. We want to evaluate this investment opportunity today. Today is when we are making the decision, invest or not invest, right? So in today's dollars, how much is this whole investment worth? How much are we getting back total in today's dollars, evaluated in today's dollars? In other words, we need to find the present value of multiple cash flows, right? This problem is on finding the present value rather than the future value. You can imagine a timeline under which you can put the numbers that are given, and now we have a lot of information that's given. Under year 1, which is at the end of year 1, you can put $200. Under year 2, $400. Under year 3, $600. Under year 4, $800. And you can place the question mark under year 0, which is today. In other words, you need to find, how much this is all worth today. Well, just like with the future value of multiple cash flows, let's find the present value of multiple cash flows by doing the calculations we know from chapter 5, where we were working with single cash flows. So let's break it all into pieces. We have 4 pieces here, 4 different dollar amounts. Let's first look at $200 and ignore the rest. What is the present value today of next year's $200, right? In other words, receiving $200 in a year is just like receiving something today, right? What is the equivalent of 200? That would be today's dollar amount instead, right? Following the present value formula from chapter 5, you would take $200 and divide it by 1 plus the interest rate. The interest rate in this problem is 12%, so you can divide by 1 plus 0.12 or simplify to 1.12. The answer you get is $178.57. In other words, what this means is receiving $200 back from this investment in 1 year is just like receiving $178.57 today. You can also do it in the financial calculator by pressing 200, making it negative, the plus minus key. Then you press the FV key to tell the calculator that this number is my future value. Then you press 12 and IY key. So you have just told the calculator that 12 is my interest rate per year. And then you press 1N. So you just told the calculator that 1 is the number of years in the future. Compute present value, right? The same way you find the present value of $400 that you would be receiving in 2 years. Following the present value formula from the previous chapter, you do 400 divided by 1 plus the interest rate to the second power, which is 1 plus 0.12, that whole thing raised to the second power. Or it can be written in a shorter way, 400 divided by 1.12 raised to the second power. This gives you $318.88. Again, what 318.88 means is receiving $400 in 2 years, right? So waiting for 2 years to get $400 is just like not waiting at all and instead getting slightly less money. You're equally happy with these two options, right? Option 1 being 400 in 2 years, option 2 being 318.88 today, right? So 318.88 is the present value of $400 that you would need to wait 2 years for to get. Again, this could be done in the financial calculator. This time you would use 2 for your N. Then $600 received in 3 years. You find its individual present value. Make sure you change the power to 3, or in the financial calculator, change your N to 3. And lastly, you find the present value of $800 to be received in 4 years. And here, the correct power in the formula would be 4. And in the financial calculator, 4 would be your N, number of years. So we have 4 individual present values, which essentially mean receiving 200 after 1 year, 400 after 2 years, 300 after 600 after 3 years, and 800 after 4 years, right? Is just like receiving these 4 individual present values that we just calculated today, all of them today. You're equally happy with these 2 options, the today's option and the delayed option, right? So now we can answer the question, how much is receiving these 4 different amounts which were given to us worth, which would then tell us how much, what is the maximum we would be willing to invest into this investment opportunity today. You simply add up the 4 individual present values and get their sum equal to $1,432.93. This is the answer to the problem. You would not want to invest more than this amount. If you do, you would be losing money. You would invest more than how much you get back. If you invest less, if it's possible, then that's a great profit opportunity for you. Here's another way this problem could be solved. So actually, let me go back to the previous slide. And I will bring up my financial calculator right here. So let's turn it on. Let's make sure everything is cleared. The way I do it is I do a full reset. I press second plus minus, which brings up reset right above it, and then enter. So turn it off, turn it back on. We are now sure that everything is cleared from the calculator's memory. Here's how you can actually do the present value of multiple cash flows in just one step, right? Remember, you cannot do that for the future value of multiple cash flows, but you actually can do that for the present value of multiple cash flows. One step. We're going to use what we call in finance cash flow keys. Press the button that means cash flow, right? We're going to enter our cash flows that are given. Press the button in the second row that says CF, cash flow. Start with that. What does the display show? It shows CF subscript 0 equals 0. What it means is the calculator informs you that cash flow for year 0, which is given, is $0. This is something we can keep as is, if it's true, or this is something that we can change. Should we change it? No, because there's nothing you receive right away. We're not given any cash flow for today, right? Just like, 200, 400, 600, 800. There's nothing today. So we leave it as is. but we want to save it. So you press the button enter. And a little thing appeared on the display, a little extra, like a triangle. It basically means that it has just been saved as $0 for year 0 cash flow. What do you do next? You press the down arrow key in the first row of your calculator. What has just happened? The display now says C01 0.00. This is now cash flow, next cash flow that we would like to enter, right? We're going to be entering essentially 4 cash flows. What's cash flow in year 1? So what's the next cash flow? That's what we now would need to change to 200. So you put 200. You don't change it to negative like we were doing in chapter 5 for future value or present value calculations. You just leave it as is. And you save it by pressing enter again. Now, kind of imagine you're building this table on a piece of paper. You're writing down several rows, right? 1 row per cash flow. So you press the down arrow key again. You kind of want to go to the next line below. But you would expect to see cash flow 02 or something like that, CO2, but it doesn't tell you that yet. Instead, what you see is F01 equals 1. What do you think that could be? F stands for frequency. How many times? So how many times in a row do we have $200? Only once, right? Because another example could have $200 repeating consecutively, but we don't have it here. So this is usually the case in a lot of our problems. And so we want to leave it at 1. So we want to tell the calculator that yes, frequency of 1 is correct. Let's save it. Press enter. Now the down arrow key, after pressing that, now you are asked to enter your cash flow number 2, which is $400. So you press, just like you did with $200, you now repeat the same steps all over again. You press 400, you don't change any signs, leave it as is, because you can think of it being the money you receive rather than spend, right? You press enter to save it, down arrow key, it asks you for the frequency. Again, we only have $400 once consecutively or like total in our problem. You enter, you save it by pressing enter. Down arrow key again. What's cash flow number 3? That's $600. Repeat the same steps. 600, enter, down. It's only once. You press enter again. And actually, you can skip the enter for the frequencies. You can just press the down arrow key, essentially twice in a row. Down, then cash flow number 4. That's the last one we have, $800. You press 800, enter, down. And like I mentioned earlier, you can do enter down, or you can just press the down arrow key one more time, because this is the default. It will be saved as the default value of 1. Cash flow 05, what is it? We have no more cash flow 5, right? That's it. We only had 4 numbers. What do we do next? Now, after we have just entered all the cash flows that are given to us, now the only thing that's missing is we want to tell the calculator that we want to apply a 12% discount rate for every single one of these given cash flows. And then we want to find their combined present value using that discount rate. So first you tell the calculator what it is you want to do with these cash flows, and we want to find their combined present value. Find the key in the second row of the calculator, which says NPV, net present value. Here in this problem, the meaning of it is combined present value. So press that. The display shows I equals. I is like IY, interest per year. You need to specify what the interest rate is per year. That's 12% in this problem. You press 12, enter, right? You don't press IY because the calculator already tells you that that's going to be your interest rate. So you just press 12 and then enter, which is what I did. And then press the down arrow key and then press compute. $1,432.93, just like on the slide. Okay, and I explain the same exact steps here. So these are the steps I went through. Okay. Next example. What if we change things a little bit in the example we just did? What if the cash flows are paid at the beginning of each year? In other words, we move all the numbers closer by 1 year. So we wouldn't need to wait 1 year to get the first cash flow, $200. We would get it right away. As soon as we invest money, we immediately get $200. And we would get $400 in just a year, and so on. How would we solve this problem? Well, there are several different ways. We can do 1 year at a time like we did before. What's the present value of $200? It's $200. It's already at present. Then we would discount $400 back by 1 year, $600 back by 2 years, and $800 back by 3 years. Or, right, what I did here. That's one way of doing it. And you would get $1,604.88, right? So that's 200, present value of 200, it's 200, plus 400 divided by 1.12, plus 600 divided by 1.12 squared, plus 800 divided by 1.12 cubed to the third power. Notice how the answer we got is higher than in the previous problem where it was only a little bit over $1,400. Why does it make sense? Because, so why is it that when you get the money sooner, the present value is higher? Well, think about it. You get the money sooner. That's better, right? We all want to get money sooner. So that's the intuitive explanation. But mathematical explanation is that we don't need 1 year of discounting applied to each of our 4 cash flows, right? We have used no discounting for $200. Only 1 instead of the previous 2 years of discounting for $400. 2 instead of 3 years for $600, and 3 instead of 4 years for $800, right? Another way of solving this problem is to realize that, well, what I have just explained, you are removing 1 year worth of discounting. So you're reducing the number of years over which we discount each of the future cash flows by 1, which means the same thing as taking the answer we had on the previous slides for the previous version of this problem, and then bringing it into the future by 1 year. So that's mathematically how we can undo 1 year of discounting. So you do $1,432.93 multiplied by 1 plus the interest rate, which is 1 plus 0.12, or simply times 1.12. And this is how you get the same result, $1,604.88. In the financial calculator, how would you do, this? So by the way, this is where if you clear by pressing second and FV, clear time value of money, it does not clear everything. For example, if you press on the cash flow key, and you can actually now keep pressing the down arrow key, it will show you what is still saved. See, it never got cleared. And this is where I do a full reset of my calculator. I press second, plus minus, enter. And now if you press the cash flow button and then start pressing the down arrow key, everything is back to zeros, right? So everything we just did on the previous slides is gone. Now we can start fresh. Okay, how do we start fresh? We press the cash flow key, right? Cash flow 0 means what do we have in year 0? And this time it's no longer nothing because we have just shifted everything, closer by 1 year. Everything is 1 year sooner, which made $200, receivable today. So that's our cash flow 0. Now we need to change it to 200. Press 200, enter. Down arrow key. Cash flow 01. What's the first cash flow in the future? That's $400. So just like before, press 400, save it by pressing enter, press the down arrow key. What's the frequency of that first cash flow in the future? $400 is only once, it's not repeated again in the following years, so we'll leave it at 1. And you can either press enter and the down arrow key or just the down arrow key. The calculator will keep 1 for your frequency. Cash flow 2, that's the second one in the future. That's year 2 on our timeline. We change it to $600. Press 600, enter, down, leave the frequency at 1 again, press the down arrow key again. Cash flow 03, the third one in the future, which is our fourth cash flow that's given, $800. Just like before, press 800, enter, down, down. What's cash flow 4? That would be the fifth one that is given to us. We don't have anything like that. We are done with entering the cash flows. Now we want to tell the calculator, I want you to give me their combined present value at 12% discount rate. You press the NPV button in the second row. It asks you for the I, which is the interest rate. Put 12, enter. Now you have just saved it. Down arrow key, compute. $1,604.88, just like on the slide. And I review the cash flow keys in the financial calculator on my next slide. So this is exactly what I just did. Next example. Your broker calls you and tells you that he has this great investment opportunity. If you invest $100 today, you will receive $40 in 1 year and $75 in 2 years. If you require a 15% return on investments of this risk, should you take the investment? If you did not know anything about, finance, present value, future value, and anything like that, you would kind of look at just the dollars that are in front of you. And you might think that, oh, I spend 100, but I get a total of 40 plus another 75, which is 115. I get 115 back if I just invest 100. So at the first glance, it might seem like a great investment opportunity. But what we have learned over the last lectures is that this may turn out to be wrong, and that's all because of the interest rate. The interest rate determines how much the future numbers are worth to you now, right? What would be an equally, good scenario, right? So instead of waiting, how much would you get now and be equally happy? In other words, the right way to approach this problem is to look at $40 and at $75 and calculate how much they're worth to you today. Find their combined present value. If the number you get is above $100 that you would need to spend now, then it's a great investment opportunity. If the combined present value is less than $100, it means it's a bad investment opportunity because you would be spending $100 for something that's worth less than that, that would not give you that money back. You would actually lose money. Okay, so how much is receiving $40 and $75 worth to you today? You can also rephrase it and ask the following question. If you could instead receive one equivalent amount today, how much would it be? One amount that's reflecting both 40 and 75 received in the future. So $40 will be received in 1 year, $75 in 2 years. This is what is given. You can find the present value of $40 by taking 40 and dividing by 1.15. That would give you $34.78. In other words, if you didn't have to wait a year, how much money received today would make you equally happy, right? So you would be equally happy if you did not have to wait a year to get $40 and receive today $34.78. That's the present value of next year's 40. Similarly, you find the present value of 75 years. To get it, you would need to wait 2 years. If you did not want to wait 2 years, how much could you receive today that would make you equally happy? That's finding the present value of 75. You take 75, divide by 1.15 squared. Again, what's 1.15? It's 1 plus 0.15, which is 15% annual interest rate in decimals. And the second power indicates how many years in the future $75 is at. So the present value of $75 is $56.71. If you combine them, you get the sum of $91.49. What does it mean? It means this investment that offers you to wait a year and get 40, to wait another year and get 75, is equivalent to receiving cash right away, today, immediately, which is $91.49. You are equally happy between getting this one amount now and the alternative scenario, which is $40 in 1 year and $75 in 2 years. And of course, we can do this whole calculation rather than in 3 steps. We could do it all in 1 step if you use the cash flow keys. So let me bring up the financial calculator. Let's make sure we clear everything. Second, plus minus, enter. Cash flow. Nothing in year 0. You leave it at 0. You press enter. Down arrow key. That $40 is our first cash flow in the future. You press 40, enter, down. The frequency of it is 1. You leave it at 1, you press either enter down or just down. Cash flow 02, the second cash flow in the future. That's 75. 75, enter, down. It's only once, you press the down arrow key. No more cash flows. Now you press the net present value, NPV button in the second row. I, that's the interest rate. That's 15% per year. It's given to us. You press 15, enter, down, and the last thing you do is press compute. 91.49, $91.49. And you already probably read the conclusion, the answer to this problem, because you would be investing $100, which was given to us today, for something that gives you back an equivalent of $91.49 today. It's not worth it. You would be overpaying about $8.50, right? You should, as we say in finance, reject this investment opportunity, because you would be paying $100 for something that is only worth $91.49 today. We are done with, on the previous slides we did the future value of multiple cash flows and the present value of multiple cash flows. Now let's look at some special cases. We're going to look at we're going to first look at the future value of multiple cash flows, which are all the same amount. All cash flows are the same dollar amounts. This is what is known as annuity. It's defined as a series of cash flows of an equal amount at fixed intervals for a specified number of periods. So there are three things that go into this definition of the term annuity. First, cash flows of equal amount. They must all be equal. For example, $4,000 over and over and over and over again. At fixed intervals. It means they're all spaced out equally. Let's say once a year. So there's nothing somewhere in the middle after 6 months. We're not skipping any here. And the third thing, for a specified number of periods. This tells us that we don't have them forever. They stop at some point. Let's say we have them for 20 years, once per year, and that's it. There are actually a lot of annuities in real life, and you may, never realize that this is, an annuity. For example, a lot of you may have purchased a car using a car loan. How do car loans work? You borrow some money that pays for your car, but in return you'll be paying back monthly payments to your lender. Typically the monthly payments would be the same, identical dollar amount, so maybe $250 a month for, let's say, 5 years. So we have identical cash flows, they're once a month, and everything stops after 5 years or 60 months. Other loans, for example, you take a loan to buy a house, a home mortgage loan. Maybe it's for 30 years. Again, home loans require you to make the loan payments back to the bank every month, equal amounts of money, typically, and it will all end at some point, let's say after 30 years. That would be 360 months. So 360 identical monthly payments. You're renting an apartment, probably most of you do. You probably signed a lease, maybe for 2 years, maybe for 1 year, more, maybe for 6 months, as long as it's not a month-to-month lease. Under, let's say, a 2-year apartment lease, you are expected to make the same rent payment every month for 2 years, 48 times. So same amount, once a month, 24 times. Another example is maybe paying for your car insurance. So maybe you pay twice a year. So you're making semi-annual payments for your car insurance, maybe for a few years. And then maybe your rates go up. Some people earn their salary monthly under some contract. Some earn bi-weekly, so every 2 weeks, let's say on a 5-year contract. That's also an annuity. Property taxes, if the value of your house doesn't change, you will be paying the same taxes every year. So same number once a year. And for how long? Until you sell your house. That's when it will all end. I have different examples here, and you might realize that some examples have monthly payments, others have bi-weekly payments, others have semi-annual payments or annual payments. These are all annuities. In fact, the word annuity is kind of misleading because it kind of makes you think of something annual, right? Occurring once a year. No, it doesn't have to be once a year. As long as it's the same, time intervals, it's all annuities. It could be daily, weekly, bi-weekly, monthly, quarterly, annual, biannual, every 10 years, etc., etc., etc. Let's look at this first example of an annuity. And we are now looking at future values. And you can probably guess what's going to be on later slides. We're going to be looking at annuity present values. So let's start with annuity future value example. You want to deposit $4,000 at the end of each year for the next 20 years in a bank account paying an 8% annual interest rate. How much will you have in 20 years in your bank account? Well, based on what we know, this is how we would set it up. So you would imagine this timeline. You show years in the future, years 1, 2, 3, all the way to 20. And under end of each year, you put $4,000, right? So you have $4,000 20 times in the future. And you place the question mark under year 20. So at the end of the 20th year, how much do you have total in your bank account? How would we calculate something like this on the earlier slides in this chapter? You would break it into pieces, right? That's what I taught you. You would first look at the first $4,000. What is its future value at the end of the 20th year, counting from today? Well, you would take 4,000, multiply by 1 plus the interest rate and raised to the power that indicates the number of years over which the interest will be earned. Notice that the power is 19, it's not 20, because 1 year is already elapsed. There are 19 years remaining between end of year 1 and end of year 20. And this is the correct power to be used for the first cash flow. And the interest rate was given at 8% per year. So I do 4,000 times 1.08 raised to the 19th power. Second $4,000. Again, we find its individual value at the end of the 20th year, counting from today. Between end of year 2 and end of year 20, there are 18 years. So this will be the power for this future value. 4,000 times 1.08 to the 18th. The next 4,000 will be, treated the same way. For its individual future value, the power will become 17, and so on. One before last, at the end of year 19, it only has 1 year to earn interest, and so we use no power at all. Or you can put power 1, it's the same thing. And the last deposit that you will make, $4,000 at the end of the 20th year, it's already where you want it to be. So it doesn't earn any interest. You deposit, immediately after that you check how much you have in your account, and from just this deposit you have $4,000, no interest on top. So you essentially broke it into 20 pieces, right? 20 individual future values, and then you add all of them up. Takes a while, possible to do, but it will probably take you, I don't know, a few minutes for sure. And just hope you don't make any mistakes somewhere. Turns out there is a compact formula for annuities, which looks like this. In our problem, you would take $4,000 for this repeating cash flow. You would multiply it by 1 divided by the interest rate, 0.08. Then what you get is multiplied by the next big term. In the big parentheses we have 1 plus 0.08 interest raised to the 20th power, and then you subtract 1. The answer would be $183,047.86. Notice how this is significantly more than simply taking $4,000 and multiplying by 20 times, which is $80,000. It's over $100,000 more than $80,000. Why is that? Interest. Interest, interest on interest, interest on interest and interest, and so on. So the extra $103,047.86 is pure interest, nothing else. Interest that you get from the bank. And you can also do it in the financial calculator. So if you go back to our problem, let's bring up the calculator. Let's clear everything. Second, plus, minus, enter. We're going to learn a new button now. And the button is called PMT. Third row, second from the last. What do you think it stands for? That's right, payment. That's the dollar amount that's repeated again and again, the annuity payment amount. You put 4,000, we have many of those, and we want to find their future value, combined future value. So before you would say 4,000 as your PV, but we're not going to do it this way. We're not going to use PV button at all, because we have a whole bunch of PVs, right? 20 of those. Instead, we're going to call it payment. You press the PMT button. Before you press the PMT button, change 4,000 to a negative 4,000 by pressing plus minus key. And then press PMT. So now the calculator knows that you have $4,000 or whatever the units are, and that's going to be repeated a number of times. It's an annuity problem. How many times does it repeat? 20 times. You press 20 and then you press N. So here the interpretation of N is slightly different from the way it was used in the previous chapter to find the future value or the present value. Here N means how many repeating payments we have, because technically $4,000 earns interest 19 times, so that's the right N we used for the first $4,000. The second $4,000 will be earning interest 18 times, so that would be the right N, the way we know what N is, from before. So we cannot like put a whole bunch of N's like 19, 18, 17 and so on. Instead, N, when we are working with the PMT button, N changes its meaning to how many repeating numbers we have. So we put 20N. Then the interest rate, 8 IY, as always. That's it. We don't need any more information. We have $4,000 repeating every year. The annual rate is 8%, and we have a total of 20 of those repeating cash flows. Then we press Compute FV. And this is the number we got, earlier, right? So this is exactly the same result, 183,047.86. That's in dollars. And the steps I just showed in the financial calculator are all repeated here. The PMT key is the new key we have just learned. And N now means how many cash flows we have. Interest rate just, stays as is. This is the general formula. It finds the future value of an annuity with T many cash flows evaluated at the end of the Tth period. So you take, the annuity payment, which is labeled as C, stands for cash flow, multiplied by fraction 1 over R, then multiplied by open parenthesis 1 plus R, that term raised to the Tth power, then you subtract 1, close parenthesis. The way this formula is written is it kind of uses this multiplication factor, the cash flow that's repeating times something else. And this something else, this complicated term with fractions, powers, and parentheses, is known as the future value, interest factor on an annuity, or FVIFA for some interest rate R and number of cash flows T. And again, there is a table at the end of the textbook, Appendix 4, which gives you the value for this whole future value interest factor on an annuity for different combinations of interest rate R and number of cash flows T. But I'm not using it in class because, financial calculators are a lot more easier, faster, and more flexible. They allow for more cash flows than what that table shows, and it allows for a wider range of interest rates, like, partial interest rates, like, let's say 5.1%. In the table, you would only see 5% or 6%, but nothing in between. Let's do another example. Suppose you begin saving for your retirement by depositing $2,000 per year in a retirement account. These days, the best rate you can get is around 3% per year. How much will you have in 40 years? So actually, let's click on this. That's something I found you know, for the investment accounts. So that's actually very recent summary of interest rates, February 2019. And if you scroll down, it gives you different banks and what they offer if you deposit money for a long term. And you would see that, you know, for a longer number of years that the money gets deposited for, the interest rate is somewhere around, you know, 3%, a little bit more, a little bit less. So let's make it, you know, kind of easier and say 3%, which is what I did. So you're putting $2,000 per year in a retirement account. You will expect to earn 3% every year on the money that you have. And the question is, how much will you have in this retirement account after 40 years? This question is asking you to find the future value of this annuity with 40 identical annuity payments in the amount of $2,000 each. So following the formula to find the future value of an annuity, you do 2,000 multiplied by 1 divided by 0.03, the interest rate, times open parenthesis 1 plus 0.03 raised to the 40th power minus 1 close parenthesis. This gives you $2,000 times the entire second complicated term is 75.4, like the multiplication factor. You can, for example, find it in table 4 at the end of the textbook, or calculate the whole thing by hand, or using, you know, a calculator that allows for parentheses and all that. The answer is $150,802.52. And in the financial calculator, let me bring it up, you would do the following. Let's clear everything just to make sure nothing gets messed up. So $2,000 is going to be repeating. When you know something is repeating, that's PMT, the payment. 2,000, make it negative. PMT key. The interest rate is 3%. 3 IY. We have a total of 40 identical deposits. So you put 40 and compute FV, future value. 150,802.52. Again, notice how much of a difference the interest makes. So if you didn't know this formula, the easiest way you would be trying to solve it is taking 2,000 multiplied by 40. That would be what? That would be $80,000, right? 80,000. We have almost double that. We have 150,802.52. So the rest is all interest earned over the years. Another example. You decided to start saving and depositing $1,000 at the end of each month. The best checking account rate you can find these days is 2% per year. Actually, let's click on this link I found. Bankrate.com. Again, we have, you know, different banks, like a lot of online banks, and it shows the interest rate you earn on checking accounts. So we have 2.02%, 1.25%, and then very low percentages. They're actually ranked highest to lowest. So the highest is 2.02%, right? Let's make it easier and use 2%. So 2% per year. Your bank will be adding interest to your account monthly. You will be making these deposits, right, 1,000 at the end of each month, for exactly 2 years, until you graduate from Cal Poly. How much money will you have in your bank account 3 years from today? This is actually a pretty complicated problem. First, let's see what's going on. Let's draw our imaginary timeline that goes into the future. And there are 3 years in the future that are important. For the first 2 years or 24 months, you will be making the deposits in the amount of $1,000 each at the end of each month. So at the end of the first month is where you put the first $1,000. At the end of the 24th month, you put the last one. We have a total of 24 of these $1,000 months. The first step would be to find the future value of this annuity at the end of it. So at the end of the second year, which is when you stop making any further deposits. So how much do you have at the end of 24 months? And then, because the question asks us to calculate how much you'll have in your account after 1 extra year, you would then need to take the answer you get in step 1 and find its future value. You treat this answer from step 1 as a single cash flow, kind of going back to chapter 5, right? And you find its future value after 1 more year, except you should keep in mind that the interest is earned monthly, so you would need to find the future value after additional 12 months. So your N would be not 1, but 12. So in the first step, we want to find how much money we will have in our account at the end of the second year, which means at the end of 24 months. So 24 is what we're going to use for T in the future value of an annuity formula. Because deposits will be made monthly, everything should be reflecting the monthly frequency in our formula. For example, we already know that the number of cash flows should be 24. The interest rate should also be monthly. To find the monthly interest rate, you take 2% annual rate and divide by 12, and you get 0.1667%. This is a little bit rounded because it's actually 0.16666, and it just keeps going. It's sixes. When you use this monthly rate and 24 for the power in the future value for an annuity formula, you will get $24,465.67. And of course, you can do it in the financial calculator. How do we do that? Let's see. I already cleared everything, but let me do it again. 1,000 is going to be repeating. Make it negative and save it as payment, PMT key. How many times will it repeat? 24 times. Put 24 N. You need to use the monthly interest rate, which is 0.1667. We rounded it a little bit, right? And you press IY, compute future value, 24,465.77. On my slide, it's 67 cents rather than 77. On my slide, the number is more accurate because I used Excel to do the math, and Excel kind of doesn't round the numbers in intermediate steps. So the Excel actually used a more accurate interest rate where it's sixes, never ending sixes. Then the second step. What do you do in the second step? In the second step, you let's say you get kind of lazy. You're like, oh, I know that in the second step this will be my present value, so why don't I just, save myself some time and right away press the plus minus button to make it negative, and then PV. So now I'm at the beginning of step 2 of my calculations. Then I do 12 months. The money sits in the account for 12 more months, 12N, and keeps earning the monthly interest of 0.1667%. Press IY. Compute future value. Oops, I'm really off. This is not what the slide shows. I got $37,070.33 but the slides show that I should have $24,959.50. Which one is right? The financial calculator made a mistake. What's on my slide? The lower number is actually correct. So what did I do wrong with the calculator? The mistake is that I did not clear the calculator's memory. I should have cleared the calculator's memory and then did step 2. In other words, I shouldn't have, done it the lazy way. And what happened is that the calculator thought that I continue having $1,000 deposits at the end of each month during the 3rd year in step 2. But this is not what's going on, right? My PMTs were essentially 0 during the 3rd year, but the calculator used $1,000 for the payments. And so what I should have done is I should have cleared everything and then started from the beginning. So at the beginning of the 3rd year, we are now starting step 2 calculations. We have $24,465.67. Negative PV. 12 months later, 12N, at the monthly interest rate of 0.1667%, press IY key. How much will you have? Compute future value. Now the answer matches my slide's answer, except again there are a few cents by which our answer in the calculator is off. That's again the rounding error, because it's using the rounded monthly interest rate, and on my slides the number with 50 cents is actually obtained through Excel, where nothing is rounded. So this is more accurate. In other words, before doing step 2 in the financial calculator, you need to clear the time value of money, either second FV or full reset, second plus minus enter. Either way would do the trick. Another example. You're saving for a new house and you put $10,000 per year in an account paying 8%. How much will you have at the end of 3 years? A, the payments are made at the end of each year. B, the payments are made at the beginning of each year. Let's see if it makes any difference, and if so, how much of a difference. Cases A and B are illustrated here. Again, each has its own little timeline. In case A, where the payments are made at the end of the year, the first $10,000 is at the end of year 1, and then we have 2 more after that. In case B, with payments at the beginning of each year, everything is 1 year sooner, right? So if between 0 and 1 we have the first year, then the beginning of the first year is under 0 on my timeline. This is where we have the first $10,000. Everything is sooner in case B, right? In both cases, A and B, we are asked to find the future value, right? How much you will have at the end of 3 years. So we need to find the combined future value of these 3 numbers at the end of year 3 in both cases, A and B. Okay, so let's calculate case A future value. Following the standard formula that we had many times, you would use 8% for the interest rate per year, which is given, and 3 for the power in the formula. And 3 indicates how many repeated cash flows we have. So we are making 3 deposits, and that's going to be the power in the annuity future value formula. The answer we get is 32,464. And of course, we can do it in the financial calculator. First, turn the calculator on. Let's clear everything, which is always recommended. Second, plus minus, enter. $10,000 make it negative, press payment, PMT. 3 is how many of those payments we have. So I press 3N. And the interest rate is 8%. I press 8 IY. And I'm gonna compute future value. $32,464 even, right? This is the same calculations we were doing in all previous problems. And now the second case, case B. Let's see what's going on here. Everything is 1 year sooner, right? Do you think it makes a difference for the combined future value? Of course. Every single one of these $10,000 cash flows will earn interest over an extra year, right? So the very first deposit will sit in the account for full 1 to 3 years, as opposed to case A, in which the very first $10,000 will earn interest over only 1 2 years, right? And so on. And so a much easier way to find the future value for case B is to take the answer from case A, which we already have, and add in 1 year worth of interest, right? There is 1 extra year over which the cash flows earn interest, every single cash flow in our annuity. So we take $32,464 and multiply it by 1 plus the interest rate, which is 1 plus 8%, or simply times 1.08. And we get $35,061. This answer is higher than the answer in part A because of the extra 1 year worth of interest that all 3 of our deposits will earn. And what we did in this step, in the financial calculator, the way you would do this step is, let's clear everything first. You would take the answer from part A, which is behind the calculator. That's $32,464. Make it negative and set it as our present value, PV. 1 year later, right? What's the future value? 1N at 8% annual interest rate. 8 IY, compute future value. $35,061, and actually there are 12 more cents in the answer. In finance, we refer to cases A and B as an ordinary annuity and annuity due, respectively. An ordinary annuity is like an ordinary case, the standard, most typical case that we deal with. For example, a lot of problems don't actually specify when the payments are made or received, at the end or at the beginning of each time period. So if it's not specified, the default is at the end, and that's the ordinary case. That's an ordinary annuity. But the wording might give you a hint that the payments are at the beginning of the year. So maybe they say something like the first payment is going to take place immediately, or the first payment in our annuity is today. Or it could say payments are made at the beginning of each year, kind of very clearly. That's an annuity due. So the first payment is due immediately. And in the calculations you see here, the way we adjust for the beginning of the year is we take, the regular annuity future value formula and multiply it by 1 plus the interest rate, right? So we are adding 1 more year worth of interest to every, single cash flow. So just to review, annuities can be called ordinary or due. Ordinary annuity and annuity due. Ordinary annuity has payments at the end of each period, and annuity due has its payments at the beginning of each time period. You can also rephrase and say that in an ordinary annuity, the first cash flow occurs with a delay. So you have to wait one time period before you have to pay or receive the first payment, depending on the problem. And in an annuity due, the very first cash flow in that annuity is immediate. And this is the general formula which shows how we can go from an ordinary annuity future value to an annuity due future value. We simply multiply by 1 plus the interest rate. And so you can say that the future value of an annuity due is always going to be a bigger number than the future value for an ordinary annuity. That's because of this 1 plus R term. But there is another way to find the future value of an annuity due. In the problem we just did, right? We can do the following. Let's clear everything. We can tell the calculator that the calculations I'm about to do for an annuity are going to be based on an annuity due, right? And you press 4 keys. Second, payment. It brings up the text right above the key payment that says BGN, begin. And then second, enter. So basically you're saying begin, set to the begin mode. And then you can even turn the calculator off and back on. Now the display shows 3 extra letters, BGN, begin. Everything is now in the begin mode. And now, after setting the calculator to the begin mode, I want you to do what you did for an ordinary annuity, right? You did what? You did 10,000, make it negative, PMT. We have 3 of those, 3N. 8% is the annual interest rate. 8 IY, compute future value. What do we get? We do not get the answer for case A, we get the answer for case B, annuity due answer, $35,061.12. So this is probably going to be your favorite method, right? So to summarize, there are, how many methods do we have? I would say 3. One cash flow at a time. So the first $10,000, find its individual future value using 3 years, right? The second $10,000, find its individual future value after 2 years. And the last $10,000, find its individual future value after 1 year. And then add up the 3 individual future values. That's one, kind of the most time-consuming method. The second one is what I have on the slide, where you first calculate an annuity future value, but the default in the calculator is that everything is at the end of the year rather than at the beginning. So it will not give you an accurate number, and you need to then, as the second step, need to make an adjustment yourself. You take the number you got and multiply it by 1 plus the interest rate, 8%. So this on my slide is basically the second method. And the third method is where you set your calculator to the begin mode, second payment, second enter, and then do what you did for an ordinary annuity. Because the financial calculator will know that this is not an ordinary annuity that you are doing the calculations for. It's an annuity due. Okay. Then next, so we already covered the setting to the due mode. or begin mode, set to due or set to the begin mode in the calculator. Now let's look at annuities. Present value of an annuity. Let's say you have this, a very realistic situation. You're ready to buy a new car. You are driving around, shopping around, and you are choosing between 3 cars that you really liked. A Nissan, which costs $20,000, a Hummer costs $27,000, and a nice bright blue Porsche for $30,000. So these are your options, and you would like to buy one of these cars. You also know that you have no money at all. You're going to be taking a loan to fully cover the cost of whichever car you will be able to buy, to afford. But that will be determined by how much you can afford to pay per month on the monthly car loan payments, right? So a typical loan requires that you make payments back to the lender every month. And let's say your budget allows you to spend up to $600 per month on car loan payments. Let's say you have not the best credit score. Let's say it's 595. This table here, I found it on valuepenguin.com website. It shows the relationship between what kind of FICO credit score you have, like in which range you are, and for each range it shows what the annual interest rate would be on new cars if the loan is for 60 months, which is 5 years. So what is the interest rate for a 5-year car loan, depending on your credit score? In our problem, your credit score is 595. Where is it? It's in the range between 590 and 619, for which the corresponding annual car loan interest rate is 14.06%. So let's put all this information together and answer the question. Which one of these 3 cars can you afford? The question is kind of vague. It doesn't really tell you what you need to calculate, right? So how are we going to approach it? Well, with your credit score of 595, the interest rate is 14.06% per year. The loan would be for 60 months. What would be the monthly interest rate on the loan? It will be 14.06% per year divided by 12 months. It gives 1.1717% per month. And we did this because since the loan payments are monthly, everything in our calculations must be monthly. Whatever calculations we'll be doing, everything should reflect the monthly frequency. Monthly interest rate, number of months, monthly cash flow. And what we can do is, how about we calculate what the maximum loan is that you can afford? How would we do that? We can do the following. Every month, how should we think about loans? What is a loan? Somebody gives you money today, somebody lends you money, a bank, right? Some lender. And then you will be paying it back in small pieces over many, many months, maybe even years, many years. But the lender will charge you interest, right? Okay. So in a way, the loan amount should equal the sum of all future loan payments that you will be making back to the lender in return. Except the sum should reflect the whole time value of money. So the interest rate should be somehow embedded in our summation. And the way it's done is we don't just add, we don't just do $600 times 60 months, right? we discount each of the future monthly loan payment. We discount it back to today at, using the monthly rate and the appropriate number of months. For example, we don't just take the first $600 that we will be paying in 1 month and then add in the next one. The first $600 would need to be divided by 1 plus the monthly interest rate. So 1 plus 0.011717. The next $600 from the end of the second month is divided by the same thing but raised to the second power, and so on. And the last $600 in this sequence of a total of 60 loan payments is divided by the same term, 1 plus the interest rate, 0.011717 in decimals, raised to the power 60. Okay, so this is what you need to do. Very, easy, right? Well, not really. It will take you forever, right? It's very frustrating to have to calculate something like this. There are 60 terms in this sum. But don't worry, of course, there is a quick and easy solution to this. I'll show you 2 different shortcuts. The first one is the formula. It looks a little bit similar to the formula we had for an annuity future value. This is an annuity present value, the present value of all loan payments in our particular problem, which says take the loan payment, $600, multiplied by the reciprocal of the interest rate, so 0.011717. Then multiply that by, open parenthesis, 1 minus reciprocal of 1 plus the interest rate raised to the power 48, close parenthesis. That gives $25,751.77. If you go back, right, so just remember this number, $25,700 approximately. Which car can you buy for that kind of money? For that kind of money, you can only buy a Nissan, because that's the only, price that falls, under this loan limit, which was $25,000 and a little bit. You cannot afford a Hummer, a nice blue Hummer. You cannot afford a nice yellow Porsche, right? Unfortunately. Okay, so this is the formula, and it only covers the purchase of a Nissan. But of course, there's another shortcut. You can do the whole thing in the financial calculator. And based on what we were doing in on the previous slides for annuity future value, you probably have already figured out what I'm about to do. Let's clear everything. Remember, the calculator was on the begin mode. Now we need to go back to the ordinary annuity mode, and resetting the whole calculator just takes care of that. So how do we find the present value of an annuity? The present value. Annuity means we need to use the PMT button. What's our payment? That's the loan payment that we will be making every month for the next 5 years or 60 months. So we put 600, we make it negative, we save it as our payment, the PMT key. How many of those will we have? We will have them over 5 years, but everything we are entering should reflect the monthly frequency. So 5 years is 60 months. 60 N. And the interest rate is also monthly, which is 1.1717, and then you press the interest per year button, I/Y. Compute. This time you're pressing the present value key, $25,751 and a little bit. That's only enough to buy, the cheapest one of the 3 car choices that you had. right? So this is how you do it in the financial calculator. This is what I just did. There's actually another way of doing it. See how many different ways we came up with? There's a way to do it in the financial calculator using the cash flow case. Maybe I should, open up this slide and do it here. So how else can we do this? We can use the cash flow case. Let's clear everything. Start all over. Cash flow. What's cash flow zero? What kind of payments are we going to be making on the loan? We're not going to make anything right away. We can wait a month before we pay the first $600. So we save it as $0. We keep it as is. We press enter. Down arrow key. What's our first cash flow? Cash flow of 1. The first one in the future. That's the first $600 payment. You put 600, keep the sign as positive, enter, down. What's the frequency of it? Now you can actually change the frequency. How about we make it 60? This is exactly how many times in a row we have the same exact cash flow, right? We are going to be paying $600 60 times in a row, consecutively. Same number every month, over and over and over for 60 months. So when the display asks you for the frequency, which is set to 1 as the default, you are going to change it to 60, press enter, and then the down arrow key. What's cash flow 02? Is it $600 in the second month? No, you actually don't need anything anymore. You're done. You have just entered 60 identical cash flows, right? We are done with all cash flows. There is no more. And now you press the NPV button. It asks you for the interest rate. You put the monthly rate, which is 1.1717. Enter, down, compute. Same answer. $25,751 and a little bit, a few cents. And again, I show both financial calculator methods on this slide. So, either one is okay to use. You can use the one with the payment button, or you can use the cash flow case. It's completely up to you. Everything gives the same answer. In fact, let's check something. So let's go to this website. It's Bank of America. Somewhere on the Bank of America website, you'll find, actually, let's go to the original page. Bank of America website. Auto loans. Click here, auto loan calculator. This is where you want to be. Total loan amount. What was it? Total loan amount was let's move it here a little bit. 25,751 is what we found, right? The term is for 60 months. That's 5 years. The interest rate, this is actually per year. What was it? 14.06%, right? Calculate payment. Exactly $600, right? $600 is the required payment on a loan in the amount of $25,751. So what I'm trying to say is that all of these formulas we are learning in this class, future value, present value, future value of an annuity, present value of an annuity, everything we are learning is real. There's nothing made up or simplified. This is exactly the formulas that banks use to compute your loan payments or anything related to loans and other things in finance. So I think it's kind of cool that now you know what's behind all those loan calculators that you see online. Now you can do all that yourself. Now you can walk to a bank, ask for a loan, bring your financial calculator, and they will be talking to you differently. So in general, when you have an annuity and you need to find its present value, essentially one cash flow at a time, you discount it back to time zero using the appropriate number of time periods. And then you're combining all individual present values. And the shortcut to that is the formula I already showed you, which says the present value of an annuity equals the annuity cash flow multiplied by 1 divided by the interest rate, then multiplied by open parenthesis 1 minus, then we are subtracting a fraction with 1 on top, and on the bottom 1 plus the interest rate, and that raised to the power 4, close parenthesis. So the present value of an annuity gives the value of it in today's dollars one time period before the first cash flow. See, there's like a delay here. The very first cash flow is not today, but it's with a delay, with a one time period delay. And we're going to come back to that later. What if it happens immediately? So this is the formula for the present value of a T-period annuity. And again, there is a table at the end of the textbook which gives the value for this present value interest factor on an annuity, which is everything in the formula but the repeating cash flow amount itself, for different combinations of interest rate R and time periods T. So there is a table in Appendix A.3 at the end of the book. Again, this is optional. I'm not going to be using it in class. Let's look at, again, this is optional. I'm not going to be using this table in class. Example, let's say a family won $10 million in a lottery. The money is paid in equal annual end-of-year installments of $333,333.33 over 30 years. By the way, I got this annual payment by simply taking $10 million and dividing by 30 years. The family also has an option to instead accept one lump sum payment today, which is, by the way, how it is in real life. So next time you read about some lucky family or co-workers winning a lot of money, read the article carefully. You will always see a paragraph about this alternative option of collecting money. One large payment today and no more in the future. So in this example, how much would that one lump sum payment to be received today be? How much should it be? And we also know that the proper discount rate in this problem is 5%. So to solve this problem, we need to find the present value of all future lottery payments, which was option number 1. Because an equivalent amount of money that you could collect today should represent the sum of all future amounts of money, right? And except we cannot just add them all up. We cannot just do $333,333.33 times 30 of those. We need to add up their present values. So we need to add 30 present values. And the shortcut is how we can do it sort of in a faster way rather than finding 30 individual present values. So this is the present value of an annuity formula. So you take the annual amount multiplied by 1 divided by 5%, the discount rate which was given to us. Then you multiply that by open parenthesis 1 minus fraction which has 1 on top, and on the bottom to the 30th power we have 1 plus 5% interest, and then you close the big parenthesis. The answer we get is a little over $5 million. $5,124,150.29. So have you noticed how in this problem the family won $10 million, but if you choose option number 2, one lump sum collected today, it's gonna be just a little over half of $10 million. Everything is done correctly. This is how things work in real life too. So $10 million spread over 30 years in these equal amounts, 333,000 in a little bit, is just like receiving just a little over $5 million today. You're indifferent between the two options, collecting a little over $5 million today and instead collecting $333,333.33 30 times spread over the next 30 years. You are indifferent between these two options. And of course, in the financial calculator, you can verify this answer. Let's clear the calculator first. We need to find the present value of an annuity. So we will be computing PV. For that, we need 3 things: the payment amount, the repeating cash flow amount, how many of those we have, N, and the interest rate between all of them, which is IY. So let's start with the payment amount. $333,333.33 negative PMT. 5 is the interest rate, 5 IY. We have 30 of those payments, 30 N, compute PV. And that's our answer, $5,124,150.29, just like on the slide. Let's say there are 2 investment opportunities, A and B. A pays you $1,000 at the end of each year for 20 years. B pays you $1,000 at the beginning of each year for 20 years. The discount rate is 10%. Which one of these 2 investment opportunities is more valuable in today's dollars, and by how much? So we need to compare today's values of these 2 investment opportunities. In other words, think of it as comparing an equivalent of receiving $1,000 20 times, but an equivalent of that would be receiving one large amount of money today, right? So how much would that one large amount of money today be equal to for case A and case B? And then compare those. So in other words, compare the 2 present values. So we have an annuity going on in this problem, right? $1,000 is repeated again and again and again at the end of each year. So it's an annual repeating payment. And we have it 20 times. Same in case B. How do we find the present value of the first annuity in case A, where the payments are at the end of each year? We already know the formula from before, where we use 1,000 for the payment, 10% or 0.1 in decimals for the interest rate throughout the formula, and 20 for T, the number of payments. That gives us $8,513.56. Of course, we can use the financial calculator. Let's move it here. First, clear everything. 1,000 is our payment, so 1,000 negative PMT. We have 20 of those, 20 N, and the interest rate every year is 10%. 10 IY. Compute present value. $8,513.56. Okay, now what about case B? In the second case, if you compare, it to case A, the only difference is that since everything is at the beginning of each year, everything starts sooner. Everything is 1 year sooner. The first $1,000 in this investment opportunity will be received by you today. You wouldn't need to wait for it for 1 year, right? The second $1,000 will be received in 1 year, whereas in case A, you would need to wait for 2 years for that, right? Everything is sooner in case B. Do you value this investment opportunity in case B higher or lower? I would definitely value it higher because it's sooner. I get all my money sooner, right? I don't need to wait for it. Waiting kind of costs money, essentially. And the way we should look at how that will affect our numerical answer is we don't need to discount those $1,000 cash flows so much, right? We want to undo 1 year worth of discounting for every single one of them, right? They're not going to be discounted by 1, 2, 3, all the way to 20 years. They're going to be discounted by 0, 1, 2, all the way to 19 years. There's 1 year less of discounting for each of these 20 $1,000 cash flows. And mathematically, to undo the discounting, we can multiply the answer we had in case A by 1 plus the interest rate. So it's like we are taking $8,513.56 and bringing it into the future by 1 year, right? Because really, if you compare the timelines, case B is like, it's as if we just move the question mark in case A from, into the future by 1 year, right? This is where we want to be, where the first cash flow occurs. And so it's like we want to be in the future by 1 year. And that's this, adjustment we are doing to our calculations. So the fastest way to get the answer would be taking the answer from case A and multiplying by 1 plus the 10% interest. And we get a larger number, $9,364.92. Intuitively, the larger number in case B reflects the fact that we like this investment opportunity better. We get our money sooner by 1 year. Who wouldn't like that? And in the financial calculator, this step we just did could be done by, let's clear it all first, by finding the future, the future value of a single cash flow. So I guess in the formula I put here, it kind of looks like we are finding the present value, which is correct, but we are, finding it as the future value of, the present value we had in case A after 1 year. So it might look a little bit confusing here. Okay, so the present value of the 20 identical future cash flows in today's dollars can be found by taking the answer from part A, which is 8,513.56. Make it negative, that's your PV. And we want to bring it into the future by 1 year. So this way we are sort of adding back 1 year of discounting. We are undoing it. We are undoing 1 year worth of discounting. So I press 1N. The interest rate is 10%. I press 10 IY, and I'm computing future value, $9,364.92. And then you can compare the two results in cases A and B, and the difference between the two present values that we found is $851. So the opportunity to receive the money sooner by 1 year is more valuable by $851. Now, just like with annuity future values, annuity present values also have, two formulas. One for an ordinary annuity and one for an annuity due. Same interpretation as before. An ordinary annuity is sort of the default case when the cash flows are all at the end of each time period, for example, at the end of each year. An annuity due is when the cash flows are due immediately, so they are all at the beginning of each time period. And the transition from an ordinary annuity present value to an annuity due present value is done by this multiplication by 1 plus the interest rate. And so the present value of an annuity due is always bigger than the present value of an ordinary annuity. And something important, this was exactly the same for the future value of an annuity due versus the future value of an ordinary annuity. With future values, it's the same, result. An annuity due future value is also always bigger than an ordinary annuity future value. So it's true for both present value and future value. And again, there is a way to tell the calculator that the calculations I'm about to do are going to be for an annuity due case. So you can set your calculator to the annuity due mode or the so-called begin mode. If you go back to this slide to cases A and B, then here's what we can do. So let's reset the calculator first. Everything is cleared. Then I want to tell the calculator that I'm setting you in to the begin mode or annuity due mode. Press 4 buttons. Second, payment. Second, enter. If you turn it off and back on, you will see the small letters BGN, begin. The calculator is now in the begin mode. And then try to follow the steps that we did in part A for an ordinary annuity and see what you get. We did $1,000 for our payment amount. We made it negative. We pressed the PMT button. Then, because we have 20 of those, we pressed 20N. The interest rate was 10% per year, so we pressed 10 IY. And with this information, we wanted to compute the present value. But look at what the display gives you. It doesn't give you the answer for case A. It gives you the answer to case B, right? 9,364.92. And that's because you told the calculator before you put in all these numbers that were given that we are going to be now in the begin mode. So you can switch between the end mode and begin mode very easily by pressing second, payment, second, enter, right? Which is also explained on the bottom of slide 42. So you set the calculator to the begin mode, and then you do the calculations like for an ordinary annuity. But that gives you the answer for an annuity due. If you want to go back, then you can either press second, payment, second, enter again, and that will take you back to the ordinary annuity case. Or I just simply reset my calculator. It works even faster. let me show you the cash flow keys using the most recent problem with cases A and B. So let's look at case B, an annuity due. Clear everything, right? Actually, let's start with case A. What's going on in case A? How can you do it using cash flow keys? Cash flow 0 is nothing, so you leave it as is, press enter, down arrow key. Then we have $1,000, right? 1,000, enter, down. What's the frequency of it? It's not 1, which is the default, it's 20. You put 20, enter, down. There is no more cash flow that needs to be entered. You're done with all 20 of them. Then you press NPV. It asks you for the I, the interest rate. You put 10, we have a 10% rate. 10, enter, down, compute. $8,513.56. Now, what will be different for case B, an annuity due, with the $1,000 payments occurring at the beginning of each year? Make sure you clear the calculator, it's important. Cash flow key. What's cash flow 0? It's no longer $0. Now the first $1,000 occurs immediately, and that's what you need to put in the calculator. 1,000. Enter. Down. What's cash flow 01? The first one in the future. It's $1,000 in 1 year. You put 1,000 again. Enter. Down. What's the frequency of it? How many times in a row will we have it? The right number is 19, because the 20th, we already took care of that with cash flow 0, right? There are 19 more left in the future, 1 through 19. So this is the right frequency. Enter, down, no more. You press NPV. The discount rate is 10%, 10, enter, down, compute. $9,364.92. So maybe this is a little bit tricky in finance, that oftentimes there is no single way to solve a problem. Or maybe it's a good thing, because some of you prefer one method, others find a different method more intuitive. So this way there will be the right method for each one of you. Let's summarize annuity present value and annuity future value, like some effects of things that go into the calculations. Both annuity future value and annuity present value will be higher if we increase the dollar amount of the cash flow that's repeating. It probably makes an intuitive sense, because really future value and present value is nothing but the sum. So if the numbers you're adding up are larger, of course the sum will be larger too. And that's true for the case when we want to find the future value or the present value. The second thing that they have in common is the number of cash flows. Again, if you're increasing the number of terms in the sum, the answer will be higher. So both the future value and the present value will be increasing if you increase the number of cash flows. So that's N in the financial calculator. One thing that makes them different is the interest rate or the discount rate, the R in the formula or the IY in the financial calculator. The future value is higher if we increase the interest rate. The present value decreases if we increase the interest rate. And the last item I have to compare the two annuities is annuity due versus ordinary annuity. And this is again something that both future value and present value of an annuity have in common. Both annuity future value and annuity present value are higher when they're based on an annuity due case rather than on an ordinary annuity case. Let's do a mid-chapter summary. So in the first part of chapter 6, we talked about first how we would do the math for many different cash flows, so multiple cash flows, as opposed to a single cash flow, which was the case in the previous chapter, chapter 5. To find the future value, you can split it all into small pieces, one cash flow at a time, find its individual future value, and then add all of them up. To find the present value, you can do the same thing. You can find individual present values and then add them up. Or you can use cash flow keys in the financial calculator. Then we looked at many different cash flows which have identical values. That's what an annuity is. We looked at the future value of an ordinary annuity, where you can calculate individual future values and add them up, except that might take you a lot of time if it's a very long annuity. A much faster solution would be using the PMT key. You would enter PMT and NLY and compute the future value. To find the future value of an annuity due, you can do it in the financial calculator in the same one step using the PMT key, except you first set the calculator to the annuity due mode. As for the present value, for an ordinary annuity, the longest way would be finding individual present values, one for each cash flow, and then adding them up. A much faster way is using the PMT button, where you enter the payment, the number of payments, and the interest rate IY, and computing PV. Or you can use cash flow keys in the financial calculator. And to find the present value of an annuity due, you can do the same exact things, except if you choose the method with the PMT button, you first need to set your calculator to the begin mode. And if you want to use the cash flow keys, then the very first cash flow for year 0 should not be 0, but whatever the cash flow amount is. Now we will look at our next topic in chapter 6. What if we know the annuity value, either the present value or the future value, but instead what we don't know is, for example, the cash flow amount, the repeating dollar amount. That's C in the annuity formula or PMT button in the financial calculator. Or maybe instead we do know the cash flow amount, but we don't know the interest rate, which is R in the formula or IY in the financial calculator. Or maybe instead what our unknown is the number of the repeating annuity cash flows, which is T in the formula and N in the financial calculator. So this part of the chapter is a little bit tricky, just to warn you. If we are working with an annuity present value, let's say we know the loan amount, which is always the present value of all future loan payments back to the lender, right? So we know the loan amount, right? But now, and this is the formula we have for the annuity present value. C is the cash flow amount, which is repeating, R is the interest rate, and T is how many repeating cash flows we have. Or maybe it's a present value of an annuity due problem. So maybe it's a loan where payments are due on the first of each month, something like that. Then the formula has an extra multiplied by 1 plus R at the end of it. In either case, if we need to find for the cash flow amount, then we can mathematically rearrange it and take present value of an annuity or annuity due and divide by everything that the annuity payment is multiplied by. So we get this division. Or we can use the financial calculator, where you would be computing PMT. Then maybe instead we know the cash flow amount, we know the annuity present value or annuity due present value, but you don't know the interest rate. There is no formula that allows to easily solve for the interest rate. So you do it trial and error. The easiest way would be using the financial calculator, where you would be computing IY. And of course, there is a third thing that could be instead unknown. That's the number of annuity payments. That's T in the formula or N in the financial calculator. Again, there is no easy way to rearrange the formula. So you either do trial and error, or you can use the financial calculator, where you would be solving for N. Then this slide has basically the same things, but for a slightly different setup. A setup in which we know the annuity future value or the annuity due future value. In this case, there is a formula to compute the annuity payment, where you divide the future value of your annuity or annuity due by everything that the annuity payment is multiplied by in the original future value of an annuity formula. Or in the financial calculator, to solve for annuity payment, you would be computing PMT. Then to find the interest rate or the number of annuity payments, the easiest would be using the financial calculator and solving for IY, which is the interest rate, or N, which is the number of annuity payments. So let's think of, examples. So let's now do a few examples. And they will be basically, all over the place. In some, we know the annuity present value, in others, the annuity future value. Some are annuities due, some are ordinary annuities. In some, we need to find the annuity payment, in others the interest rate, and then yet in others the number of annuity payments. So everything will be kind of completely mixed up, messed up too. So let's start with this first example. You won a lottery, $12 million. You have two choices. First, you take $7,042,000 today and nothing else in the future, just one single lump sum payment to you. The second choice you have is you take 26 annual payments of $461,538 each. Where did this strange number come from? That's a very simple division of $12 million by 26. The question is, what is the implied interest rate? I would say for problems like this, don't rush into trying to use a calculator and solving for something. I would say first answer these 4 questions. First, probably the most important one. Are we working with the present value or the future value of an annuity? Which one is known? The second one, is it an ordinary annuity or an annuity due? Then what are we asked to solve for? And once you figure out what you need to solve for, then you should be able to then you need to figure out what it is that you would need to input in your calculator. So there are always 3 numbers that are given and the 4th one that you need to solve for. So is it an annuity present value or an annuity future value problem? The money you won, $12 million, one way to collect it is to receive 1/26 of that, of $12 million every year for the next 26 years, right? So $12 million that you won is basically the sum of the annual installments in today's dollars. So this is the present value of an annuity. So you kind of really need to understand from the wording whether this large number, which is your annuity value, is the present value or the future value. I guess here the hint is you want the money today. So anything that's today is the present value. Okay, so we answered the first question. We are working with the present value of an annuity. The second question is it an ordinary annuity or an annuity due? How can we tell? An ordinary annuity is when the annuity payments, the numbers which are repeating, are occurring at the end of each time period. For example, at the end of each year. And an annuity due would be when the payments occur at the beginning of each year. So they're due immediately. What do we have here? When would the annual installments be paid? Actually, it doesn't really say. What should we assume? The default is at the end of each year. That's always the default in finance classes. And that's the ordinary case. And that's where the name ordinary annuity comes from. So we are working with the present value of an ordinary annuity. All payments will occur at the end of each year. So to collect your first installment, you would need to wait 1 year from today. That's what it means. Then the third question I put here is, what do we need to solve for? Well, the question was about the implied interest rate, so it's pretty straightforward. We need to solve for interest rate. So that's IY in the financial calculator, if that's what you will use to calculate the answer. In the formula, that's R, which stands for rate of interest. And once you figured out what you need to solve for, then the last question I would recommend you answer to yourself is, okay, which numbers do I need to input in the calculator? So we already know that we are given the present value of an annuity. That's one. $7,042,000. Then the other two will be N, that's 26 future annual installments if you choose the second option. And the third number that is given is the cash flow amount, the annuity payment, or PMT in the financial calculator. That's the amount of each annual installment for the next 26 years. $461,538. Okay, now the easiest would be probably using the financial calculator. You input your present value, N, and PMT, and you're computing IY. So let's do that in the financial calculator. So here's the financial calculator. Turn it on. I always recommend to start by clearing everything, because even if you used your calculator last week, last time, it will still store some values unless you already cleared it. So do a full reset just to be, absolutely sure nothing is stored. Second, plus minus, enter. The only problem is if you increase decimal places, then now that drops down to 2, which is the default number. So maybe we should increase the decimal places. How would you do that? That's actually always a good idea, especially in multi-step problems. Here it's actually okay, and my answer is rounded, as you can see, to 2 decimal places, but let's say you need more than 2 decimal places in your answer. Then that's the first thing you would do in the calculator. How do we increase decimal places? Second, decimal place on the bottom. The default decimals is 2. You want to change it, let's say, to 6. Press 6, enter. You're done. Now you can turn the calculator off and back on. It's going to be calculating everything from now on until you reset it to 6 decimal places. So now let's solve this problem. 42,000, make it negative. That's our annuity present value. And you're indifferent between collecting this one lump sum amount today or instead collecting 26 annual payments in the amount for $61,538. So let's input that like second option values. So that's equivalent to collecting 26. So you put 26N. The payment amount for each installment would be 461,538. You leave the sign as is, you don't change it to negative. So kind of the way to remember it is everything that's today is one sign, everything that's in the future is with the opposite sign. So we entered our present value with the minus sign, which means we should leave the PMT with the positive sign. So I input the value and then I press PMT. Now it's stored as the annuity payment. Okay, so we put in PV, N, and PMT, and now we just press compute IY. 4.431201. If the answer needs to be rounded to 2 decimal places, then that's 4.43% per year, the annual interest rate. Now let's look at the second problem. You want to save up $60,000 for your graduate degree that you plan to start in 4 years. You keep all your money in an account that offers an 8% rate per year with the interest earned monthly. If you plan to set aside fixed amounts of money at the beginning of each month, what will your monthly deposit be? So once again, the same 4 questions. Are we working with the present value or the future value of an annuity? Is it an ordinary annuity or an annuity due? What do we need to solve for and which numbers are given? Technically, you can add a couple more questions at the beginning of that questions list. For example, I would say the very first question should be, are we working with a single cash flow or multiple cash flows? The way you know that this problem is not about a single cash flow, even though it looks like there's only one, but multiple cash flows is, again, from the wording. You will be setting aside amounts of money at the beginning of each month. So it's something repeating monthly. There are many cash flows. So it's not like a chapter 5 type problem with one cash flow. It's chapter 6 type problem with multiple cash flows. Then another extra question you could ask yourself is, now that we know it's multiple cash flows, are they different amounts or the same amounts? Well, we will be setting aside fixed amounts of money at the beginning of each month. So every month it will be the same amount of money that we will be setting aside. So it's the same cash flow. Repeating again and again. What do we call that? That's an annuity. Okay, now let's go, look at this list. Are we working with the present value or with the future value of an annuity? Which one is known? So if we want to save up $60,000 for our graduate degree in 4 years, then $60,000 is in the future, right? That's our goal for the future. That's what we want to have at the end of all of our monthly deposits. So this is, how you can understand that it's the future value that is known. So $60,000 is the future value of many, many, many equal amount deposits. And that's what the question is asking us to compute. So we are working with the future value of an annuity. We've just answered the first question. Second question, is it an ordinary annuity or an annuity due? So this refers to the timing of the repeating cash flows. When do they take place? Do they take place at the end of each time period or at the beginning of each time period? We know that we will be setting aside fixed amounts of money at the beginning of each month. The word beginning is the key word for annuity due. So we are working with the future value of an annuity due. And then the last two questions are, what is it that we need to solve for? For example, in the financial calculator, what are we going to be computing? And then the question after that is asking, what is given? And again, with annuities, three numbers are given. The fourth one is something that we need to compute. So what do we need to solve for? We need to solve for the amount of monthly deposit. That's the annuity payment. PMT in the financial calculator, or in the formula, that's capital C. Which three numbers are given? We already know that we are given the future value, and two more are how many deposits and the interest rate per time period. So there's a trick in this problem. Everything will be monthly, right? We are going to be making monthly deposits. As soon as you realize what the frequency is of your annuity payments, everything that you enter in the calculator should reflect that frequency. So for example, for your N, the number of deposits, you need to put how many monthly deposits you will have. Because in our problem, we will be making deposits over 4 years, you should put not 4, but 4 times 12 equals 48 for your number of deposits. So our N will be 48. And for the interest rate, we cannot use the 8% annual rate for IY. We need to divide it by 12 to get the monthly rate, which is 0.66667% per month. That's not in decimals, that's in percent. Okay, because it's an annuity due, the first thing we need to do in the financial calculator is tell it that we're going to be doing the calculations for an annuity due. So we say set the calculator to the annuity due mode or the begin mode. Okay, let's do that together. Financial calculator, let's clear everything. Let's increase the decimal places. Let's do 4 decimal places. Second decimal place, 4, enter. Off, back on. Let's start. How do we set the calculator to the annuity due mode or so-called begin mode? You press these 4 buttons. You press second, then you press PMT, then you press second again, and you press enter. And now if you turn the calculator off and back on, first it still remembers that you set it to 4 decimal places, and the second thing you may notice is the small letters BGN on the display, which stands for begin. We are now in the begin mode. And now let's enter the 3 numbers which are given and compute PMT. So we are given the future value of an annuity due. So you just put 60,000, change the sign to negative, and press the FV button. We have a total of 48 deposits that we would need to make in order to reach this $60,000 goal in our bank account. So you press 48 N, and the last thing is the monthly interest rate. Remember, everything should be monthly in our calculations. The monthly rate is 0.66667. So technically it's a bunch of sixes. You can just keep pressing 66 multiple times, but I round it like this. It's a little bit random, I guess. After entering the monthly rate, you press the IY button. And finally, you press compute. What was it that we are computing? Payment. Compute payment. $1,057 and approximately 72 cents, right? If you round 2 cents. Next example. You have just bought a new flat screen TV that cost $4,000. You fully financed the purchase, which means you took a loan for the full amount, $4,000. You didn't pay anything out of your pocket. The loan agreement requires you to make annual payments of $750.54 at 5% interest, with the first one due immediately. How many loan payments will you have to make until the TV loan is paid off? Again, I'm asking you to ask yourself the same 4 questions as in my previous examples. The first question is, do we know the present value or the future value of an annuity? $4,000, the loan amount, is the present value of an annuity of loan payments. You can almost remember it as a rule. Any loan is the present value of loan payments, right? So $4,000 is the PV. Then the second question I have on my next slide is, are we working with an ordinary annuity or annuity due? We know that the first future loan payment will be due immediately. So all loan payments will be made at the beginning of each month, right? Once a month. Once a year. They are 1 year apart from each other. And if the first one is immediate, then that right away should tell you that we are working with an annuity due. Then what is it that we need to solve for? How many loan payments? Clearly that's N in the financial calculator or T in the loan formula. And which numbers are we going to enter in the calculator? The 3 that are given. 4,000 will be our PV, 750.54 is PMT, and 5 is going to be our IY, the annual interest rate. So we are working with the present value of an annuity due. We need to solve for the number of payments, which is N in the financial calculator, and the numbers that we are going to enter are PV what is $4,000, IY is 5, and PMT is 750.54. From my experience, a lot of students somehow tend to solve these kind of problems where it's asking you for the number of payments wrong. I see that a lot. So the wrong way would be kind of doing it the simplest way that sort of comes to your mind. You take the loan amount, 4,000, and divide it by annual loan payment, 750.54. That gives 5.33 years. While this is intuitively the right way to look at this problem, in finance, this is a wrong calculation. The reason it's wrong is because you're completely ignoring the so-called time value of money, the whole, interest rate that the lender charges you. It's not reflected here at all. And so the correct way of doing it is, first, because it's an annuity due, you press these 4 keys to set your calculator to the annuity due mode. Second payment, second enter. Let's do that. Financial calculator, let's clear everything. Second plus minus enter. To set to the annuity due mode, you press these 4 buttons. Second, PMT, second, enter. Now the display shows BGN, begin mode. And enter the 3 numbers which are given. $4,000 is your loan amount, which is always the present value of all loan payments that will follow in the future. So you want to change your sign to negative and then save it as PV. Then the interest rate is 5%, 5 IY, that's per year, and the annual loan payment will be $750.54. So you put 750.54. You leave this sign as positive because you already changed the present value to a negative one. By the way, either present value is negative and payment positive, or the other way around. So press PMT, compute N. 6, exactly. 6 payments. The first one due immediately and 5 more in the future. 6 payments total, 6 loan payments total. And you will fully pay off your loan balance. There will be nothing left for you to pay to the lender. So if you did it the wrong way, you will be off by quite a lot. If you did it the right way, you will get 6 years. Next example. This one is difficult. I labeled it as difficult. It requires 2 steps. Let's say high school friends decided that 2 years from today they will take a graduation trip to Europe for the entire summer, which is 3 months. For this trip, they decided to start saving money by depositing altogether, so 2 friends combined, $200 at the end of each month into their joint savings account that pays a 12% interest per year. So it means 1% monthly. The rate is way too high, but it's just in this example to make the math easier. They will spend the entire saved amount during their summer trip in Europe. Here's the question. How much money, and it needs to be a fixed amount, will they be able to withdraw from their joint savings account at the beginning of each of the 3 months of their European travel? So here's what's going on. They will be making deposits for the next 2 years, once a month, so a total of 24 deposits. We know that they will be depositing $200 at the end of each month. So the first deposit that they will make will be 1 month from today, and the last, the 24th deposit, will be at the end of 2 years, which is month 24. That's the first step. What are you going to calculate here? You'll be able to calculate how much money they will have by the beginning of their trip. What the problem is asking us is how much will they then be able to withdraw at the beginning of each month during the 3 months of their travel to Europe. So the first month is between end of month 24 and end of month 25, counting from today. The beginning of that is the beginning of month 25, right? So it's under 24 on my timeline, and so on. So you place 3 question marks. And each withdrawal amount should be the same. So all 3 should be the same number. In the first step, you can calculate how much they will have saved by the beginning of their trip. So you would find the future value of an ordinary annuity with 24 monthly deposits at the end of each month. In the second step, you will then use the number from step 1 as the present value of 3 monthly money withdrawals, and you will be solving for the annuity payment, PMT, in the financial calculator. So step 1, after 2 years, after making a total of 24 deposits, $200 at the end of each month, they will be able to save $5,394.60. if you plug in the numbers into the future value of an ordinary annuity formula. Then, so of course you can do it in the financial calculator using 200 negative as PMT, 24 for your N, 1 for your monthly rate, that's your IY, and you're computing future value. The wrong way to then calculate the deposit, one of 3 equal amount deposits, is to take the total savings at the beginning of the trip and divide by 3. Because that doesn't take into account the fact that once the first amount is withdrawn, everything that remains will earn 1% interest over the next month. And then after the second amount is withdrawn, what's left earns interest again over the third month. So how do we include all of that into our second step? The correct way is to solve for annuity payment, either using the formula or the financial calculator. The important thing in the financial calculator is you need to set it to the begin mode. You need to clear it first and set it to the begin mode. The reason you need to clear it is because there will no longer be any additional deposits made during the 3 months after the last deposit is done. The reason you need to set it to the begin mode is because the friends, while they're in Europe, will be withdrawing money at the beginning of each month. So in a way, there are 4 steps that you need to follow to solve this problem. Okay, so let's do it in the financial calculator. Let's clear everything, second, plus, minus, enter. Step 1, how much will they have in their savings account by the beginning of their trip? We need to compute the future value of an ordinary annuity. The annuity payment is how much they will be depositing each month. That's $200. So I press 200, I change the sign to negative, and then I press PMT. How many deposits will they make over 2 years? Because the deposits are monthly, we need to stick to the monthly frequency throughout all of our calculations. And the number of deposits should be 24 N. Then we need to enter the interest rate that the money will be earning in the bank account until the friends leave for their trip. Again, the interest rate must be monthly, which is 1% per month. You put 1 IY, and you're computing future value, $5,394.69, right? 94.69. Actually, I have only 6, so you can, feel free to add 9 here. And then we want to clear everything. Second, plus, minus, enter. We want to set the calculator to the begin mode because the next step will be an annuity due. You press 4 buttons. Second, payment, second, enter. And now do the second step and the last step. By the beginning of the trip, they will have $5,394.60.6. Make it negative, save it as your present value, because that's kind of the sum of the 3 money withdrawals before they are done, right? Before the money is withdrawn. So that's the present value in the second step. That was the future value in the first step, but that's the present value in the second step. Then we're going to be withdrawing money 3 times. put 3N. The money that remains in the bank after each amount is withdrawn will earn a 1% interest every month, and we should take that into account. So you put 1 IY, and you're computing PMT. $1,816.12, and my answer is actually rounded to the whole dollar, 1,816. A pretty complicated problem. I promise I won't ask you anything like this on any exam, but it's good to see how complex things can get. And I also thought it's a pretty realistic problem, right? Saving money for something and then figuring out how much you can use out of it, regularly, if that needs to be in fixed amounts. So we are done with annuities, solving for annuity future value, annuity present value, annuity payment, annuity interest rate, and number of annuity payments. Now we are going to look at the next topic in this chapter, perpetuities. Something perpetual, something that never ends, keeps going, right? Perpetuity is defined as a perpetual series of cash flows of an equal amount at fixed intervals. Basically, it's exactly the same thing as an annuity that continues forever. There is no end to annuity payments. Keeps going forever. Okay? Let's say we have a perpetuity with some repeating cash flow that keeps going forever, and we want to find the present value of the whole endless sequence of these cash flows. If we were to do it one by one, right, individual present values and add them up, we would do the first cash flow in the future discounted back by 1 year. So we divide it by 1 plus the interest rate, plus the present value of the second cash flow 2 years from today, or 2 time periods more generally from today. You take cash flow, divide by squared 1 plus r, right? 1 plus r to the power 2. Then you do the same for the third cash flow in the future, using the power 3 in the denominator, plus the present value of the fourth cash flow in the future, right? Where you use power 4 in the denominator, and so on forever. Where do you stop? You never stop. You should keep adding all those terms, right? So is there a way to simplify it? Yes. The simplest formula you will ever see in finance. The present value of a perpetuity is equal to the cash flow, which is repeating forever, divided by the interest rate. One thing you may notice is that this perpetuity present value formula gives you the today's the sum of all future cash flows in today's dollars, one time period before the very first one, right? So if it started immediately, then in this formula you would need to just put plus cash flow. So you would have C divided by R, and then you would add cash flow. But technically you can even call it a perpetuity due. That's something I sort of made up at some point. But the book doesn't even talk about anything like this. So this is pretty much, what the book says for perpetuities. The first cash flow is not immediate, but with a 1 time period delay, and the present value of that endless sequence is C divided by R. What would be an example of a perpetuity in real life? There are actually not that many real-life examples of perpetuity. There's something called preferred stock. So some companies have 2 different types of stock shares. One known as common stock, where the company would be paying dividends that are neither guaranteed nor of equal amount. So maybe today it pays a $1 dividend on each share, next time it pays nothing, then nothing again, and then pays a $3 dividend per share, and so on. So it kind of fluctuates and is not sort of regular. Preferred stock is another type of stock that exists for some companies. That's when a company promises to preferred stock holders a fixed dividend every period, usually every quarter, forever. Right? So as long as the company is around, it will be paying the dividend to the investors forever. And not just the dividend, it's going to be a fixed dividend. So it's the same dollar amount forever, which makes it a perpetuity. Let's look at what we are given for this problem. A company sells preferred stock for $80 a share. So we know the price per share. Its offered dividend is $3, paid once a year. The discount rate is 4%. The question is this stock priced correctly, or is it overpriced, or is it underpriced? Overpriced means $80 is way too much. It should cost less than that. Underpriced means $80 is too cheap. It should cost more than $80. So how about we use the information that we are given to calculate how much one share should cost. And because we are dealing with preferred stock, which is a perpetuity, we can simply find the present value of a perpetual stream of $3 using 4% for the discount rate. So $3 divided by 0.04, that's 4% interest rate in decimals, gives us $75 per share. So you should not be willing to pay more than $75 for getting back $3, at the end of each year forever, when the company generates a 4% return on its money every year. What do we know? We know that the shares are sold for $80, right? Which was given. That's way too much. That's $5 more than anybody should be willing to pay. Are the shares priced correctly? No. They are way too expensive. They are overpriced. They're sold for $80 while their true value is only $75. So they're $5 overpriced. By the way, technically, we can use the financial calculator for perpetuity problems, although you're probably realizing it's not worth it because it's a very simple formula. You can do it by hand in just a few seconds. But okay, let's say you're curious. Can it be done in the financial calculator? Yes. Because a perpetuity is like an annuity with endless cash flows. For your N, put a few nines, like 999. I think if you put way too many nines, it will get confused and give you an error message. So put 3 nines, it's good enough. Or, because we are solving for perpetuity present value, which is like the present value of an annuity with many payments, you can also use cash flow keys, like we learned for present values of multiple cash flows. Again, here where it asks you for the frequency of your $3 cash flow, put a few nines. 3 nines should be good enough. Put 999, and then when you find the net present value, it will give you pretty much $75. So you might be off by a couple of cents. Actually, let's try that. Let's try using the annuity keys. Let's clear everything. Second, plus, minus, enter. Let's actually increase the decimal places just to get an idea how far off we will be because of the rounding error. And why is there going to be a rounding error? Because technically n is not 999, it's infinity. But 999 is a good approximation. So let's see how far off we will be. Let's increase the decimal places. second decimal place, let's make it 7. Enter. Our payment is $3 every year forever. 3, make it negative, press PMT. 4 is the interest rate per year, 4 IY. For our N, we're gonna put 3 nines, 999. N, compute, present value. See, we basically get $75 and 0, after the decimal place up to 1, 2, 3, 4, 5, 6, 7 decimal places. So probably in, a much higher order decimal place, we're going to see something other than 0. But, you can see how 999 for infinity approximation is perfect. Now let's instead try the cash flow keys. Let's clear everything. Let's again increase the decimal places. Second decimal place, let's make it 7. Enter. Cash flow keys. You start by pressing the cash flow button, CF. You don't get $3 paid to you right away, so you save cash flow for times 0 as $0. Enter. Down. Cash flow number 1 in the future. That's your first $3 dividend that will be paid to you. You press 3, enter, down. Now it asks for the frequency. How many times in a row are we going to have the $3 amount? The default is 1. We need to change it to technically infinity, but I'm going to prove you that putting just some large enough number will be fine. Let's put 999. Enter, down. NPV, the interest rate per year is 4%. 4, enter, down, compute. Again, we get basically $75 even. Technically, you would see numbers other than 0 somewhere in higher order decimal places, but in the first 7 decimal places, it's a 0. So it's perfect. 999 could be used, in place of infinity if you wanna, use the financial calculator whenever you can, including perpetuities. My suggestion would be, just stick to the formula, do it by hand. I think it's a lot faster. Next example, you just paid $750,000 for a financial security that will pay you and your heirs $42,000 a year forever. What rate of return are you earning on this policy? The word forever should right away tell you that we are working with a perpetuity. You just paid $750,000. It happened now, so that's the present value. This is the present value. We already know what it is. $42,000 is something that will be paid a year, right? So repeating every year, forever. So that's the perpetuity payment. Right? So we have the present value of the perpetuity equals the perpetuity cash flow divided by the interest rate R. We are given the perpetuity present value and we are given the cash flow amount. So what we need to solve for is the rate of return. We need to rearrange this little formula to solve for R. We can solve for the interest rate by dividing the perpetuity payment by the present value of a perpetuity. So we have just rearranged the present value of a perpetuity formula, which is C divided by R, to solve for R. R equals C divided by present value of a perpetuity. And then we just plug in the numbers that we are given. There are only 2 numbers that we need to solve for the perpetuity interest rate. 42,000 divided by 750,000, which gives 5.6%. So that's the annual interest rate. In general, there are only 3 things that could be required to be solved for in a perpetuity problem. Either we find the present value, which is C divided by R, or we know the present value and we know the perpetuity payment, like in the last example, and we are asked to solve for the interest rate R, or we know the interest rate R, we know the perpetuity present value, and instead we are asked to solve for the perpetuity payment. C equals PV multiplied by R. So these three formulas are actually the same one formula, just rearranged differently. It's really the same one formula. The next topic is called growing annuity and growing perpetuity. This is like a little bit more complicated, well, probably a lot more complicated, right, than what we just did. So think about the cash flows in our annuity or perpetuity being not constant, but instead growing, but following some pattern. They're growing at the same rate every time period. For example, a growing annuity. What would a growing annuity look like? Let's say there are 4 annuity payments. So normally we would say that they are the same amount, right? But now we are saying that the first annuity payment is this much money. The next one is some percentage larger. So to find it, we would take C and multiply by 1 plus G, where G is the percentage increase. Then the third one will be larger again. So we can change the power to 2, right? C multiplied by, open parenthesis, 1 plus G, close parenthesis, second power. And then the fourth one in our growing annuity will be calculated the same way, except the power would be changed to 3. There is a way to simplify this whole thing, and it actually looks a lot like the present value of a regular annuity, except we have the growth rate in the annuity payments reflected in the formula in a couple of places. So you would do the annuity cash flow, C, multiplied by the fraction with 1 on top and on the bottom, R minus G. Then you multiply by, open parenthesis, 1 minus. The term raised to the power T has on top 1 plus G and on the bottom 1 plus R. And you close the parenthesis. Unfortunately, you probably expect me to say, don't worry, we can solve it in the financial calculator. No, not this time. This time I'm going to tell you that this could only be done by hand. This is probably the most complicated formula you will see in this class. No, actually there'll be one more, but it's okay, I'm not going to scare you with that yet. At this point, this is the most complicated formula in this class, and you have to use it by hand, unfortunately. Future value of a growing annuity. Technically, there is a formula to find the future value of a growing annuity, but it's not in the book and we're going to skip it, so don't worry about it. Present value of a growing perpetuity, where the perpetuity payments are growing at the same rate over and over and over forever. Again, we can start with the present value of a perpetuity formula that we had earlier, which had C divided by R. And now the way we adjusted for the growth in the cash flow amounts is on the bottom where you used to have R, you now have R minus G. So that's it. So you have C divided by R minus G on the bottom. The only little rule with this formula is that R must be bigger than G. Otherwise, let's say R and G are equal. Then on the bottom you have 0, and you cannot divide by 0. Or if the growth rate in cash flows is higher than the discount rate, then on the bottom of the formula you'd have a negative number, and dividing by a negative number would give you a negative perpetuity value, which kind of doesn't make sense. It's like it costs a negative amount of money, right? So you don't pay some money for it, but instead somebody pays you to buy it. So it kind of becomes a nonsense. So R must be bigger than G. That's the only little rule. For the purpose of this class, it will never come up. In all problems on growing perpetuity, your R will be larger than your G. So this issue will never come up. By the way, you might be wondering why I never talked about the future value of a perpetuity or a growing perpetuity. That's because in the future, and by future we usually mean when everything ends. So when does a perpetuity end? It never ends. So if you imagine some point of time after 1,000,000 years where this perpetuity supposedly ends, even though even that is kind of a wrong thing to say, then by that time, each cash flow will earn so much interest and interest on interest that each will turn into a perpetuity, like infinitely much money. And you have infinitely many of those, infinite amounts of money. So we never actually talk about future value of a perpetuity or a growing perpetuity. It's just going to be an infinity. Let's look at this example. Your grandfather left you an inheritance that will provide an annual income for the next 10 years. You will receive the first payment 1 year from now in the amount of $3,000. Every year after that, the payment amount will increase by 6%. So this is how you know it's a growing annuity. The question in this problem is, what is your inheritance worth to you today? So the question is asking you to find the present value. If you can earn 9.5% on your investments. So we need to find the present value of a growing annuity, with the first annuity payment being $3,000 and every payment after that, so another 9, increasing by 6%. You need to use the formula where you plug in the numbers and solve it by hand. So 3,000 times 1 over 0.095 minus 0.06. Then you multiply by the whole thing by, open parenthesis, 1 minus, fraction to the 10th power, where in the numerator you have 1 plus 0.06, and on the bottom you have 1 plus 0.095. The answer you get, or should get, if you did everything right, is $23,774. So this is the value of this inheritance in today's dollars. Let's summarize what we have learned in this chapter so far. We looked at multiple cash flows, present value and future value. Then we looked at a special case of multiple cash flows when all of them have the same dollar value. So they're the same amounts of money. That's an annuity. An annuity is defined as identical cash flows, regular frequency for a limited amount of time. We looked at how to find the future value of an annuity for an ordinary case and annuity due case. Then we looked at how to find the present value of an annuity, ordinary annuity versus annuity due. Then we had several examples on computing annuity cash flow, which is PMT in the financial calculator, annuity interest rate, which is IY in the financial calculator, or instead the number of annuity payments, which is N in the financial calculator. A special case of annuities is a perpetuity. That's when we have an annuity that never ends. So cash flows keep going forever, right? They last forever. We only looked at how to find the present value of a perpetuity. because the future value of any perpetuity would be an infinity, an infinitely large number. So we never even have examples on that case. But we did have an example on finding the perpetuity payment when we do know the annuity present value. Another problem would be solving for perpetuity interest rate, which is IY in the financial calculator or R in the formula. For perpetuities, using the formula by hand, which is PV equals C divided by R, is much easier than doing the math in the financial calculator. In the financial calculator, what do you use for the number of payments? Technically, it's infinitely many payments, but if you just put a few nines, let's say 999, then you will get your answer. It's gonna work. And lastly, we looked at special cases of annuities and perpetuities, which are called growing annuity, growing perpetuity. That's when the cash flow amount is growing at a certain rate every time period. We only looked at the present value formulas for growing annuity and growing perpetuity. Effective annual rate, or EAR. The idea is the following. When interest payments are received more than once a year, interest rate effectively earned over 1 year will be higher than the stated interest rate. Why is that true? That's because of the interest on interest, the extra money that you would be able to earn over 1 year. And so what we need to do is, or what we're actually going to learn now is how we convert the interest rate per year, which is given to us, the so-called stated interest rate or the quoted rate, into the effective annual rate, EAR, that, that correctly reflects all the additional interest on interest that's going on. And then later, we will look at how the effective annual interest rate can be used as the correct interest rate in all the calculations which we have just done to find the present value or the future value of a single cash flow or of many cash flows or of annuities or perpetuities. Let's look at the following example. Let's see what the effective annual rate is all about, based on this very simple example. You deposit $100. The quoted annual rate is 10%. So you deposit $100 in your bank account now. You wait 1 full year until the bank transfers you your earned interest, 10%. So at the end of the year, you have $110, which is calculated by taking the $100 that you started with and adding 10% interest to it. So 100 times open parenthesis 1 plus 0.1 close parenthesis equals 110, right? In this case, interest is paid annually. Once a year, you see more money in your bank account. Let's change it a little bit. Interest is paid semi-annually. What does it mean? It means that you don't need to wait for 1 full year to see more money added to your bank account. After 6 months, you already have a little bit more. After another 6 months, you earn your partial interest again. So essentially, we are splitting the 10% interest over 1 year into 2 parts. 5% after the first 6 months and the other 5% after the second half a year. Let's do the math. Are we going to get $110 after 1 year? Let's see. You deposit $100 today. How much will you have in 6 months? 5% more, right? Which is half of the annual interest rate. And so you take 100 multiplied by 1 plus 0.05, and that's how you got 105, right? $105. Then $105 remains in your bank account for another half a year. So it gets reinvested for another 6 months. And now at the end of the year, you have another 5% on top of 105, not on top of $100. So what's the additional 5% of 105? It's additional $5.25. At the end of the year, we have 105 from 6 months earlier with 5% added to it. So you have 105 times, open parentheses, 1 plus 0.05 equals $110.25. So with the annual compounding of interest, when you have to wait 1 full year to see the interest added to your account, you get $110 at the end of the year. With semi-annual compounding, you get $110.25. There's additional 25 cents. It's just a little bit, but it's something. And so the effective annual interest rate is additional, earning 10.25% on your money, rather than earning just 10%, which is the quoted rate. 10% and a quarter is the effective annual interest rate, EAR. And I also show how you could calculate $110.25 slightly differently, where you basically say that on your initial amount of money, $100 deposited now, you earn a 5% interest once, and then you earn a 5% interest for the second time on top of what you had, half a year earlier. So $100 times 1 plus 0.05 raised to the second power. In general, in order to calculate the effective annual interest rate, EAR, when interest is compounded m times a year, we follow this formula. EAR equals, open parenthesis, 1 plus a fraction with quoted interest rate on top, m on the bottom, close parenthesis, the whole thing is raised to the power m, and then we subtract 1. So the fraction inside the parenthesis, which is quoted interest rate per year divided by m times per year, is nothing but interest rate per compounding interval. In our example with a 10% annual quoted rate and semi-annual compounding, we earn half of the annual rate after the first half a year, which is 5%. Then m is how many times interest is earned or compounded within a year. In our example with semi-annual compounding, it's twice a year. Now, let me show you how you can do this thing in the financial calculator. Let's turn it on. Let's clear everything just to make sure it's not going to reuse something that we have stored. Second, plus minus, enter. Let's increase the decimal places. Second, for decimal place, let's make it not 2 but 6. 6, enter. And now let's see how we can go from the 10% quoted annual rate to the 10.25% effective annual rate. You do the following. Second, 2. It brings up the text in the second row. That's what the key second really means. What does it say in the second row? Like right above the key with the number 2 in it. It says ICONV, which stands for interest conversion. So we want to convert our interest from the stated interest rate or the quoted interest rate to the effective rate. Take a look at what the display shows. NOM. Press either the up or the down arrow key. Just keep pressing. You will see that the display switches between 3 things: NOM, EFF, and C over Y. So go back to where it says NOM. NOM stands for nominal. It's the same thing as quoted or stated rate, the one that's given, the one that does not reflect any additional interest on interest going on. So you want to set the nominal interest rate in your financial calculator to 10. Press 10, enter. It's saved. Now press either the up or the down arrow key, right? And stop when you see C divided by Y, C/Y. It stands for compounding per year. What should this be changed to? With semi-annual compounding, or twice a year that the interest is earned, you want to set this to 2. Press 2, enter. So we enter 10% quoted rate. 2 times per year is how often the interest gets compounded within a year. And now press either the up or the down arrow key and stop when you see EFF on the display. It stands for effective. All you have to do now is press the button compute. The display now shows 10.25. The effective annual interest rate is 10.25%, which matches what we have on the slide, right? If your quoted interest rate is 10%, then we can think of other compounding frequencies. So we had annual once a year and semi-annual twice a year. And the ER would be 10%. If it's just once a year, then the effective rate is the quoted rate. And with semi-annual compounding, it's 10.25%, which we have just calculated. How about other frequencies? Well, you can think of, for example, earning interest quarterly, once a quarter, which is 4 times a year. In this case, the effective rate will be 10.381%. Or monthly, which is 12 times a year. The effective rate is even higher, 10.4713%. And this is actually very common in real life. A lot of things in life assume monthly compounding. Loans, credit cards, rents, most things are monthly, compounded monthly. Then you can think of weekly compounded or 52 times with an even higher effective rate. Daily, 365 times, even higher effective rate. The special case is called continuous compounding. That's when the frequency is basically infinity. In the calculator, you can basically change your frequency to, let's say, a bunch of 9s. It will work, or the formal formula looks like this. Exponent, and then you use the quoted rate, 0.1 in our example, and then from the whole thing you subtract 1. This is sort of as high as it can get, 10.5171% per year. Let's try one of these. So let's see once again how everything can be done in the financial calculator. Let's clear second, plus, minus, enter. Let's increase the decimal places. Second decimal place, let's make it 6. 6, enter. And now let's convert the quoted interest rate of 10% into the effective annual interest rate. Using, which one should we do? Let's do the monthly compounding, the one I said, which is very common in real life. Monthly compounding means 12 times a year. So after the first month, you have a little bit more money. Then that larger amount stays for another month and earns interest. And there's now interest on interest going on, and so on. In the financial calculator, you convert using the following steps. Second, 2. What's the nominal rate? That's the one that's given, 10%. You press 10, enter. Then either up or down arrow key. Keep pressing. Stop when you see compounding per year, C over Y. You want to change it to 12 times a year. 12, enter. Then again, either up or down arrow key. Stop when you see EFF, effective. All you need to do now is press compute. 10.471307. In my table, I rounded it to 4 decimal places for the monthly compounding, so it only shows 10.4713, but it's basically the same thing. In real life, I already mentioned there are a lot of examples of where interest rate is compounded more than once a year. Car loans, the payments on car loans, the payments on home loans, payments on any kind of loans are monthly. When you put money in a bank account, you deposit money, the bank actually calculates daily how much you earn in interest, except it waits a month before it transfers the whole earned interest to you. So the banks actually, all banks actually use daily compounding of the money in your account. Example, quoted annual rate is 6%, compounded monthly. What is the effective annual interest rate? If you use the formula, then the quoted rate would be 6% or 0.06 in decimals. M is 12 because monthly compounding means 12 times per year, and your answer will be 6.1678%. In the financial calculator, you do the following. Let's clear everything we had earlier. Second, plus, minus, enter. Let's not worry about changing the decimals, increasing the decimals. Let's leave it at 2. So you press second, 2. The nominal rate is 6%. You put 6, enter. Press the down arrow key or up arrow key, either one. Stop when you see compounding per year. You want to change it to 12 times a year, monthly compounding. 12, enter. Then either up or down arrow key, keep pressing. Stop when you see EFF, effective. Press compute. 6.17% per year, right? It's actually rounded to the second decimal place. The more accurate percentage would be like on my slide, 6.1678%. So it's a little bit below than what the calculator gave us. The important thing you should realize is that with compounding more than once a year, effectively you're earning more money. So let's say you are saving money in some bank account. Do you want compounding to be more frequent or less frequent? The answer should be more frequent because you want to earn as high interest rate as possible. Now let's think of a different example. You are taking a loan. You're borrowing money. Do you want the interest rate on your loan to be compounded more frequently in 1 year or less frequently? The answer this time should be less frequently because you want to pay a lower interest rate on the money that you borrowed. So it kind of depends which side you're on, whether you're a saver or a borrower. When the question is, should compounding be more frequent or less frequent, right? What is APR, annual percentage rate? It's the same thing as quoted rate or stated rate or nominal rate, which is how the financial calculator calls it. This is what the term that banks use. If you go to Bank of America website or Wells Fargo website, they call their interest rates APR. And this is actually the rate that banks are required by law to report to their customers. So you will always see the APR on your checking account, savings account, credit card, and so on. To find the interest rate per each compounding time interval, which is the period rate, you take the APR per year and divide by the number of periods per year. You should never divide the effective rate by the number of periods per year. It will give you a slightly higher number than the correct interest earned over each compounding interval. Example, a bank charges 1.3% per month on car loans. What does it mean? What is this bank going to report to customers by law? It's going to report the annual interest rate, or the APR, annual percentage rate, of 15.6%, which is 12 times 1.3% per month. But if you take a loan to buy a car, if you leave a balance unpaid for 1 full year, are you going to be asked to pay another 15.6% on the amount that you owe? No, it's going to be more than that. It's calculated according to the effective annual rate, right? So how do we get 16.77% per year? We just use the EAR formula. By the way, banks call it APY, annual percentage yield. So APR is like the stated quoted nominal rate. APY is the effective rate. And of course, we can verify this result in the financial calculator. Let's clear everything first. Second, plus, minus, enter. Let's increase the decimal places this time. Second decimal place, let's make it 6, enter. And now let's convert the APR of 15.6% into the effective annual rate, which should be always a slightly higher number. Second, 2. What's the nominal rate? 15.6. I press 15.6, enter. Then down arrow key again. I stop when I see compounding per year. I change it to 12. 12, enter. Down arrow key again. One more time. I stop when I see effective and I press compute. 16.765178% per year. This is the effective rate. If you round it to 2 decimal places, you will get 16.77%, like on my slide. So this rate, the banks are not required to report this higher rate to their customers, even though this is technically the true interest rate that you owe on your balance after not paying it for 1 full year. You may or may not see it on your bank's page, but banks are only required by law to report the APR, sort of the underestimated one, the lower one of the two. Let's look at this example. You deposit $1,000 in a bank account with stated annual interest rate of 8% compounded quarterly. How much money will you have in your account in 5 years? So clearly there's compounding going on quarterly, so you probably will need to calculate the effective rate. But this is not what the question is asking. This actually is a 2-step problem. In the second step, you're asked to calculate the future value after 5 years of $1,000 that you put in your bank account today. So how should we solve this problem? The first step, we calculate like by how many percent per year does your money really grow when we account for the quarterly compounding. And it's going to be a little bit more than 8%. So step 1, we calculate the effective annual rate. We can use the formula, use 4 for M and 8% for the quoted rate. That gives us 8.2432%. And then we use it in the second step to find how much you have in your account after 5 years. So we are using the effective annual rate to calculate the future value. And the effective annual rate is going to be our interest rate in the formula. So we have the future value in 5 years equals $1,000 multiplied by 1 plus 0.082434, and you close parentheses and raise the parenthesis term to the power of 5. The answer you get is $1,485.90. This is one way to solve this problem, and you can do both steps in the financial calculator, right? There is a different solution, which is a lot easier. You can first realize that we have a total of 20 quarters over 5 next years. Then every quarter you earn a 2% interest rate on your money, which is 8% per year divided by 4 quarters. And then in the third step, you find the future value after 5 years using 20 quarters for your number of time periods and 2% quarterly rate for the correct interest rate. And you find the same result. So in the second solution, you skip calculating the effective annual rate completely. You don't even use it. Example, what is the maximum you should be willing to pay for an investment that pays $1,000 at the end of each year for 10 years, if the interest rate is 5% compounded daily? What is the main question that we are answering here? The maximum you should be willing to pay for an investment. So that's today's value of some future amounts of money you'll be getting back. You'll be getting back $1,000 every year for 10 years. So this is an annuity problem, and we need to find the annuity present value. Okay, what are we going to use for the annuity PMT? $1,000. What are we going to use for the annuity N? 10, because we have 10 equal payments made to us. What are we going to use for the annuity IY, interest rate? 5%? No. We need to account for the daily compounding. So it's actually going to be something a little bit higher than 5% effectively. How much? Step 1, calculate effective annual rate using 365 for your compounding frequency. Of course, you can use the financial calculator where the nominal rate is 5, compounding per year is 365, and you're computing the effective rate. We get 5.1267% per year. It's a little bit higher than the quoted rate of 5%, which is how it should always be. And then in the second step, you use the effective rate as the interest rate to find the annuity present value. So your annuity payment is $1,000. Your annuity interest rate IY is 5.1267, which is the effective rate, and the annuity number of payments is 10 as given. Compute present value. The answer is $7,674. Let's do this in the financial calculator. Let's start by clearing everything. Second, plus, minus, enter. Let's increase the decimal places. Second decimal place, let's make it 6. 6, enter. Step 1, calculate the effective rate. You press second 2. The nominal rate, which needs to be entered first, is 5% quoted rate, which is given. You put 5, enter. Press either up or down arrow key and stop. Keep pressing and stop until when you see compounding per year, C over Y. Change it to what? Change it to daily compounding. How many times a year is that? 365. So press 365, enter. Well, technically there are leap years every 4 years with 366, but in finance we just kind of agree to always use 365. Okay, so we entered 365, we pressed enter, now it's saved. Now you press up or down arrow key and stop when you see effective on the display. Press compute. 5.1267, and we actually have a couple more, 50, which we don't have on the slide. So this is the effective rate. Okay, now let's clear everything again. Let's increase the decimals. Second format or decimal place. Let's make it 6 again. 6, enter. Let's start. We need to calculate annuity present value. So we will be computing present value. For that, we need to enter N, IY, and PMT. What is our N? We have a total of 10 future payments that will be made to us on the investment we are buying now. So put 10 N. How much are we going to be paid every year? $1,000. Put 1,000, change the sign to negative, and save it as PMT. And last but not least, what's the interest rate? That's the effective annual rate from the first step of our calculations. Put 5 point, remember we don't use decimals, so you need to kind of move the decimal place by 2 to the right. 5.1267. 5.1267. And I think we also had 2 more numbers when we did it in the calculator, which were 50. So let's do that. That's our interest per year. Compute PV. $7,674, like on the slide. And we also have some cents, approximately 43 cents, rounded to the second decimal place. So this is a two-step problem in which the effective annual rate is the first step you do, and that's part of a much bigger problem, something like find annuity present value, or a different problem would ask you to find annuity future value, or maybe find the present value of multiple cash flows, or future value of multiple cash flows, or something with perpetuities. In the previous problem, what if $1,000 that will be paid to you every year on the investment you will be buying now will never end? That's a perpetuity. Same first step, find the effective annual rate with daily compounding. We already know that it's 5.1267% per year. And in the second step, you use this as the discount rate to find the perpetuity present value. The perpetuity present value formula says take the perpetuity payment and divide it by the interest rate or discount rate. The perpetuity payment is $1,000. The correct discount rate is the effective rate from the first step, 5.1267%. The answer we get is $19,506. It's probably rounded a little bit. Example, you manage a local Bank of America branch. You want to offer a new credit card to your customers that would bring a 15% return per year. Interest is compounded monthly. What APR will you be required to report? So, a card that would bring a 15% return per year, from the bank's perspective, is the true interest that the bank makes by offering such credit card. So here, 15% is actually the effective annual rate. And the question asks us to calculate the APR, which is the nominal, the stated, the quoted annual interest rate. So we need to go back from the effective rate to the stated rate using monthly compounding of interest. How do we do that? To go back from the EAR, effective rate, to APR, annual percentage rate, we can take the formula we had earlier for the effective annual rate and rearrange it so we can have APR equals and something on the right hand side. When we rearrange the terms, we get the following: APR equals M multiplied by, in the parentheses we have 1 plus EAR all together raised to the power 1 over M, and then we subtract 1, close parentheses. In the financial calculator, you actually use the same keys, except you enter the effective rate and the compounding per year, and you're going to have to compute the nominal rate. The answer in our problem is 14.06%. So see how it's a little bit below the 15% effective, which should always be the case. The effective rate is always higher than the stated rate. So let's see how the financial calculator does it. Clear, second, plus minus, enter. Let's increase the decimals. Second, decimal place. What should we make it? Let's make it 7 for a change. 7, enter. Now we have 1, 2, 3, 4, 5, 6, 7 decimal places. Okay, let's go back from the effective annual rate to the annual percentage rate. So the number we should get will be smaller than the 15% effective rate, which is given to us. How do we convert interest rates? We press second and 2, as always. Except now, leave the nominal interest rate information as is. Right away, press either the up or the down arrow key. Keep pressing, stop when you see effective. This is 15%, which is given. Press 15, then press enter. Then press either up or down arrow key. Stop when you see compounding per year. We have monthly compounding of interest in our problem. So change this to 12. Press 12 and then press enter. And finally, press the up or down arrow key. Stop when you see nominal, and all you do now is press compute. 14.0579003. So we are keeping 7 decimal places, right? If you round it to 2 decimal places, it's approximately 14.06%, like on my slide. Let's look at this example that the textbook mentions. Payday loans. What are payday loans? It's very short-term loans made to consumers, often for less than 2 weeks. So you borrow money now, you pay it back within 2 weeks. And there are some companies that specialize in such payday loans, such as AmeriCash Advance and National Payday. How do they work? You walk in one of such companies' offices, you say you want to borrow money, you write them a check today, which is post-dated in the future. You give it to them, and they give you cash. So you have just borrowed money from them. And on the payday, on your payday, when you know you will have money from your job to pay back the loan, the company you borrowed the money from cashes your check. For example, you write a check for 120, dated 15 days in the future, which you know is when you will get your, money from your employer. Today, this payday loan company gives you $100 in cash. So you have just borrowed $100 today, and in 15 days you will pay them back $120. So $20 is basically the interest you're paying them. If you go to www.nationalpayday.com, the website for one of such companies, you will see this very happy couple. I wonder why they're so happy, because if I were them, I would be definitely crying. And you'll see in a second why. If you click on FAQ on that page, it will explain in very small font how they do their math, how much they charge, depending on how much you borrow and for how many days. So for example, you can borrow $100 for 16 days. You will be charged a $25 loan fee, and so the check you write them that's post-dated by 16 days should be for the amount $125. You can also borrow $200 or $300. So it's all very small amounts of money. That's what this business is about. You borrow just a little bit that you need. The fees are pretty high though, right? So let's look at the worst case scenario. You borrow just a little bit, $100. They charge you a loan fee of $25. So after 7 days, you will be paying them back $125. In the last column, you see the APR corresponding to this case equal to $1,303.57%. That's per year. Let's see how they got this number. You borrow 100, they charge you a $25 fee. 7 days later, you pay them back $125. It's nothing but a 25% interest for 7 days. You know, think about what the interest rate is on, let's say, car loans these days. It's like maybe 4 or 5% per year. This is 25% for 7 days. So it should already look pretty alarming, right? Okay, what does it mean in terms of the APR, annual percentage rate? What's the daily rate that you're being charged? 25% divided by 7 days, that's per day, and then you multiply it by 365 days. And that's how we get 1,303.57% per year. But wait a second, this is not even the true interest rate you're charged. Imagine you borrow $100 and you forget to pay it back for 1 full year. You're not even going to be charged 1,303.57% on $100 that you owe them. You're going to be charged even more. So it's the effective rate that we need to calculate. What's the effective rate? The stated rate that goes into the formula, or the nominal rate in the financial calculator, is 1,303.57, right? That's in percent. Compounded per year is 365 times. You do the math and you get something unimaginable. The effective annual interest rate is 36,524,696% per year. It's probably hard even to imagine what it really means, but what it means is something like this. If you borrow $1 from this company and forget to pay it back, right, after 7 days, they will come back after 1 year. Of course, they're going to wait 1 year, right? They're going to want to get as much money from you as they can. So after 1 year, you will owe them $365,247.96. That's from $1 you borrow now. So that's how big of an effect the interest compounding makes when it's so often every year. So when it's daily, it's it's a big difference, right? The big difference between the APR, the annual percentage rate, which is the quoted rate, and the true or the effective rate that you're charged on your money. Let's do this in the financial calculator. Let's increase the decimal places. Second decimal place, let's make it 6. Enter. We want to convert the interest rate from APR to EAR. Press second 2. The nominal rate is 1,303.57. 1,303.57. Enter. Down. Compounded per year is 365 times. 365. Enter. Down. When you see effective, you should stop and press compute. 36,524,191.73%. It's pretty close to what I have on my slide. So we are off in the last three digits for the interest rate and in the decimal places. So the reason why we got a rounding error is because the APR 1303.57% is rounded to the second decimal place. So if I increase my decimal place before I calculate 1303.57%, right, then I would see several more numbers after the decimal place. And if I use them as my nominal rate in the EAR interest conversion, I would get exactly the number on my slide, which is perfectly accurate, which says 36,524,696%. On these remaining approximately 15 slides of Chapter 6, I would like to cover different types of loans. There will be some calculations, but nothing that we have not seen before in Chapter 6. And I will go through the calculations, but on the exam, there will not be anything requiring math, so just sort of conceptual problems on these topics. So different loan types. It came up a few times throughout Chapter 6 that when we deal with loans, when you borrow money, let's say to buy a house or to buy a car or something else, then the loan amount should be viewed as nothing but the present value of all future payments that you will be making back to your lender. And because all payments are identical, this is nothing but an annuity. So any loan is the present value of an annuity of loan payments. In general, we can classify loans into three different types. First, pure discount loans. This means that you borrow some amount of money today, and after a while, maybe after a year, you paid back, so the principal that you borrowed, you paid back to the lender with some interest on top of it, so at some interest rate. And there's nothing going on between the time you borrow and the time when you pay the money back. That's pure discount loans. The second type of loans is interest-only loans. That's when you do pay something in between. So you pay principal at the end. So the entire amount that you borrow now, you pay that full amount at the very end when the loan is due. And in between, you're also paying interest. So maybe it's a 3-year loan, then you'll be paying interest amount in dollars once a year, and the principal at the very end. The most common actually type of loans, at least consumer loans, are like car loans, home loans, that people like us will probably deal with at some point in our life, are known as amortized loans or amortizing loans. And this is kind of the most complicated type out of these three. That's when each time you make a payment back to the lender, you are paying interest amount and part of the principal. So the fact that you're paying principal regularly means that the amount that you owe to the lender goes down with each payment. So now let's see how each of these works. Pure discount loans. So again, you borrow money today, you pay it back in one payment, which includes the money that you borrowed plus the interest on top. So a single lump sum payment. And where is this type of loans common? It's common for government bonds, which is a way for the US government to borrow money, also known as treasury bills or T-bills. And the duration of the loan is just a few months, so under a year, which means the government borrows the money, let's say, from you, and in, let's say, 12 months, in one payment, it gives that amount back to you with some interest on top. So let's look at this example. We have a treasury bill, a T-bill, that promises to repay $10,000 in 12 months. The market interest rate is 7%. How much will this treasury bill sell for in the market? In other words, what this question is asking is, how much does the US government borrow with each of these T-bills, right? By borrowing, it's basically selling it, and the money it receives from whoever buys the bond is the loan that was made to the US government by that buyer of the T-bill. So how much will the bill sell for in the market? $10,000 is in 12 months. It's in the future, so it's like what will be paid later, and we need to find how much is borrowed today. And remember, what's repaid is a single lump sum payment, which includes the amount that was borrowed, or in other words, how much the bill sold for today, plus the interest amount on top. So $10,000 is interest plus the how much was borrowed by the government. And the way we calculate it is really simple calculation. So it's in a way what we were doing in chapter 5, going back to chapter 5. You have future value of $10,000. You wanna bring it back by 1 year. So we discount it back by 1 year to find the borrowed amount of money. In the financial calculator, 10,000 is the future value, IY, interest per year, is 7%, and the number of years is 1, because 10,000 is repaid in 1 year. We compute the present value. So the answer is $9,345.79. That was pure discount loans. Second, interest-only loans. These are a little bit more complicated, but not by too much. That's when you borrow money today and you pay the principal at the end, just like with the pure discount loans, but you don't pay the interest together with the principal in one shot at the end, but you pay it regularly in between. A lot of corporate debt works this way. So corporations take so-called interest-only loans, which require them to pay interest each, let's say, year, and they pay back the money that they borrowed with the last interest payment at the end, maybe in a few years. Let's see how the math would work here. Let's say a company borrowed money for 5 years. It's a 5-year interest-only loan. The interest rate is 7% per year. The principal amount, in other words, the amount that the company borrowed, is again $10,000. So let's just use the same numbers as much as we can throughout this entire topic on loans. Interest is paid annually. The question is, what would this stream of cash flows look like? In other words, how much would this company that just took this loan be paying during the first year, during the second year, third, fourth, and fifth years? Right? Year 0 is today. That's when we borrow the money, and then we make the payments over the next 5 years regularly, and we pay interest every single year, so 5 times, and at the end of the 5th year we also pay the principal amount. In other words, how much we borrowed in year 0. So we borrowed what? 10,000, right? Which is given. What is the interest that we will be paying every year for the next 5 years? We use the interest rate of 7%. 7% times $10,000. That's how we calculate it, which gives $700 every year. So year 1 we pay 700, year 2 we pay 700, year 3 we pay 700, year 4 we pay 700, year 5 we pay 700, and we also pay $10,000 that we borrowed today. So the 5th year payment is the largest one because it includes 2 parts, and it's a total of $10,700. And now let's look at the most complicated one of all, which is probably the most common one. amortized loans. That's when we make payments regularly during the time when the money is borrowed and the time when everything must be completed, all the payments are made. And each of these regular payments includes two things: interest and principal. Home loans, car loans are examples of where you always see this kind of loans, this type, the amortized loans. There are several different versions of amortized loans. Let's look at A, B, and C, the three versions which are discussed in our textbook. The first version, version A, amortized loans, where each period, so typically loans require you to make payments every month. So let's say every month you pay interest plus some fixed amount. And this is the key here, fixed amount. Let's just jump straight to the main example I prepared. Let's make it a $50,000 loan, right? You borrow $50,000 for 10 years at 8% annual interest rate. And the loan agreement requires that you pay $5,000 in principal each year. So this amount is fixed. It doesn't change. It's constant. Plus interest for that year. And again, we want to look at what will be going on during the next 10 years. What will this firm's payments back to the lender look like? And typically what we do is we look at each year separately. For each year we look at the beginning balance, so how much we still owe to the bank, the principal payment that is made during that year, the interest payment, the total, which is the sum of the two, and then end of that year, how much we still owe to the bank. This is what is known as an amortization schedule. So it's like a table of payments over the term of the loan. So we can actually click on this Excel icon. If you double click on it, you will see, just a second, something like this. Let's make it larger. Okay, what's going on here? We have a table that shows the next 10 years, right? We have beginning balance, principal, interest, total, and ending balance. We are given $50,000, right? This is the loan amount. And at the end of year 10, we should owe nothing to the lender, right? So this is zero. So we start with 50,000, we should have zero remaining. What's going on in between? This is what we were given, right? The principal is fixed. So we are required to make $5,000 payments every year for the next 10 years, right? This is given. But this is not all we will be paying. Otherwise, it's really like, you know, splitting 50,000 into 10 equal parts over the next 10 years and no interest, right? But in real life, there's always interest that you pay to the lender. And the interest rate is 8%, which is given. So how does this, you know, affect our amortization schedule? First, we can calculate the interest paid during year 1. And what we do is actually the same thing we were doing in the interest-only loans. We take 8% interest rate and multiply by $50,000 that we owe at this point to our bank. So $50,000 times 8% interest rate gives $4,000. Okay? Now, what this means is we are paying $5,000 in principal, another $4,000 in interest, which gives a total of $9,000, right? So this is the total we are paying during year 1. Now, what is $45,000 in the last column, the ending balance? Well, this is how much we still owe to the lender. To get this number, you look at how much you owed as of the beginning of the year and how much you paid in principal, not total but principal, which was $5,000. So 50,000 beginning balance, 5,000 was paid. So this is by how much our balance has been reduced over the first year. And now what's left is 45. And you can actually notice that because we are reducing the principal by 5,000, our ending balance goes down by 5,000 every year, right? All the way down to 0 at the very end. Now, what happens during years 2 through 10? Actually, the same thing. So to find the interest, we take 8% and multiply by the balance, right? How much we still owe to the bank. 8% of 45,000 gives 3,600. Then to find the total payment that we are making to the lender, we combine the principal and the interest. The principal was given, the interest is based on how much we owe to the bank. So a total of $8,600. And so on. So we can keep doing this, for the rest of the years. So what you notice is the beginning balance goes down by 5,000, and so does the ending balance, all the way to $0 at the end of 10 years. The principal is fixed. That's the whole point of this version of amortized loans. By the way, what does the word amortized mean here? It basically means that we are slowly lowering the amount we still owe to our lender, right? So it goes down by 5,000 year after year after year in this particular example. Another thing you can notice is that interest goes down, and that should make sense because interest is calculated based on how much we still owe, which is going down. And because the principal is the same, the interest is going down, the total is also going down, just like the interest payment. So this is the amortization schedule. Another thing I did here on the bottom is to kind of illustrate how loans are dangerous for you, right? So try to avoid borrowing money as much as you can. That's the bottom line. Because even though you borrowed 50,000, you're paying it off in 10 equal components, right? A total of 50,000, which is the sum of this. But you're paying another $22,000 in interest over the years. So that's really almost half on top of your loan, right? So this is the total you're paying over 10 years, $72,000, right? So you're not paying 50,000, you're paying 72,000 out of your pocket. Okay, so this is one version of amortized loans. Now let's look at version B, where again each time period, let's say every month or every year, we are paying, making a loan payment back to the lender, which again includes two components, interest and principal, except what's fixed now is the total, the sum of the two. So let's see what that means. And I already mentioned that this is the way car loans and home loans and other, let's say, consumer loans from Home Depot, all sorts of consumer loans to purchase electronics and furniture and other things. That's how they work. Again, let's use the same information. You borrow 50,000, you need to pay it back over 10 years. The interest rate they charge you is 8% per year. We want to again see what the amortization schedule will look like. But here we are dealing with fixed annual payments. So let's click on this Excel icon. It will bring up a slightly different table, which is actually significantly more complicated. See how all numbers are kind of, there are cents and just all sorts of stuff going on, although the idea is similar. So the key here is that the total is the same. Every year you're paying the same total amount, which is still the sum of principal and interest. The total is the same, but the principal is very different each year, and interest is different too. So how do we find all this? 50,000 is how much we borrow now, right? Every year we are making the same payment. How do we find this number? How do we find that the total payment each year is $7,451.47? Well, let's use the help of the financial calculator. What is it that we need to be solving for? What is $50,000? Remember, any loan is the present value of an annuity. So let's start with that. $50,000, let's make it negative and save it as PV, present value. How many payments are we going to make? 10, right? It's a 10-year loan. 10, and then you press the N button, the number of payments. What is the interest rate that we are given? It's 8% per year. That's our IY. 8 IY. We enter three numbers which allow us to calculate the repeating dollar amount, the annuity payment each year, or the loan payment, right? So we are doing compute PMT, $7,451.47, just like in the column labeled total every year. So this is where this number comes from, right? Now, what about principal and interest? How do we split the total into interest and principal? And why is it different every year? So let's start, in the sort of opposite order. Let's look at the interest first. Interest is always calculated the same way for any type of loan. How did we do it in the earlier Excel spreadsheet? We said interest in year one is nothing but 8% interest rate multiplied by the beginning balance in year one, which is $4,000. Now we know the total, we know the interest part of the total, we can then calculate the principal part of the total. So total minus interest equals principal, right? And now that we know the principal, we can then calculate the ending balance. So we borrowed 50,000, we paid a lot of money during the first year, part of which was the principal amount, $3,451.47. So this is by how much we have lowered our like how much we still owe to the lender, right? So how much do we owe by the end of year one? 50,000 minus the principal, which is $46,548.53. And the ending balance at the end of year one is the same thing as the beginning balance at the beginning of year two. And then we can redo the whole thing all over again. We already know the total. Interest is 8% of the beginning balance in year two, which gives $3,723.88. Total minus interest gives us the principal, which then allows us to calculate the again reduced ending balance for the end of year two, and so on. So the total is the same for each year. The interest is going down because it's always calculated based on how much we still owe, which is slowly decreasing over time. Because the total is the same and the interest is going down, the principal part of the total payment is going up. But when you do the math, when you add up all the principal payments, you should get exactly the loan amount, $50,000. And once again, may notice that over the 10 years, you're not going to pay just 50,000 in cash out of your pocket. You're going to pay another almost half of that on top in interest. So you're going to end up spending close to $75,000 out of your pocket on a $50,000 loan. Okay, so that's how more common amortized loans work, such as car loans and home loans. Now let's compare the two versions, A and B. A was the principal part of the total payment was the same every year. Case B was the total, which is interest plus principal, was fixed. And the way we did the math was kind of in actually exactly the everything was done in the opposite order. In case A, we found the principal first, which was given, then interest, which is the balance times the interest rate, and then we added up 1 and 2 to get the total. Here in part B, we first figured out the total based on the financial calculator keys. So that was finding the payment in an ordinary annuity present value setting. Then we calculated the interest, then we subtracted the interest from the total to find the principal. So it was done in reversed order. Let's do another comparison of the two versions of amortized loans. Let's compare them by the beginning balance for each year. So year one, we start with $50,000 in both cases, right? That's the tallest column on the left on each graph. Then in version A, we were like climbing downstairs. It really looks like a staircase. We're going down. Each step has the same height, which was a $5,000 reduction in the loan balance every year, right? So it's like a straight line. Here in part B, in the second case we then looked at, it's kind of a strange staircase. Never, it's not something you see in real life. So what's going on here is it's like bent outwards, right? It's like a bent out curve, because we saw how in my Excel spreadsheet how when you do the math with the amortization schedule for each year, you'll realize that you're paying more and more and more in principal every year. So the principal is going up, right? The steps are getting higher and higher and higher, taller and taller and taller. And in both cases, you are paying less and less in interest with each year, because it's always based on how much you still owe, which is going down. We can also compare the two types of amortized loans by how much you're paying total every year, total annual payment. In the first case with fixed principal payments, the principal is fixed, and on top of that we add interest, which is going down over time, and so the total is also going down over time. In the second version we looked at with fixed total payments, like the name implies, the total is the same, it's flat. But within the total we can see how the interest is going down, which is actually just like in case A, but the principal is going up over time. And now let's look at case C. Amortized loans are known as partial amortization loans, also known as balloon loans or bullet loans. So there's a payment prior to amortization term, so prior to the time when the loan payments are due, like the last one when it should be made. So sometime before that point of time, you're making like a special payment, a balloon payment. Where do we see balloon payments? Actually, they're extremely common. Let's say you buy a house. Typically, people take a loan. Typical loan term is for 30 years. maybe 15, but 30 years is more common. But nobody lives in a house for 30 years. People move, they find better jobs, right? So let's say people move after maybe 4 years. What happens then? They sell their house, right? Do they get to keep all the money? No. They give back to their bank whatever they still owe at that point of time. So they pay back the remaining balance. And only what's remaining is theirs to keep. So that last big payment, the entire remaining balance, is nothing but the balloon payment or the bullet payment. There are other cases when like balloon payment takes place, but let's not worry about those. So how does it work? So this kind of shows sort of on the timeline what's going on. So let's say you take a loan for 30 years. So maybe you bought a house, you took a loan for 30 years. And so you are supposed to make a fixed total payment let's say every month, right? In real world, it's every month that you're making payments on a home loan. But you don't do that for 30 years. You basically prepay the loan at some point, much sooner. Let's say you sell your house and move away to a new house. So there is an amortization term which is used to calculate the required payment over 30 years or whatever the loan term is. But the amortization term is, but the actual loan term here is much shorter, and the last payment is much larger than all payments that have been made so far. So that's the balloon payment. Okay, let's look at the same problem. You take a loan for $50,000 for 10 years at 8% interest rate. You're required to make fixed annual payments. So essentially, this version of amortized loans with the balloon payment is just like the one we just did with fixed total annual payments, fixed total, right? In this version, in this problem on this slide, the borrower pays a balloon payment after 4 years. So maybe, it's a loan to buy a cheap house somewhere for 10 years, although it's not typical in real life. And after 4 years, we are selling the house and paying back the remaining balance to the bank. What is the amount of the balloon payment? So how much are we going to pay to the bank after 4 years? Actually, there are a couple different ways to do it. So you can either go back to our Excel spreadsheet. Let's see, I'm trying to find. Let me go back here in our previous problem, because this is where the answer is. We don't need to create any new tables. So where is the answer here? Year 4. At the end of year 4, we are making the last payment to the bank, right? How much is it? What's the balloon payment? Here it is. This is our balloon payment, $34,447.27. So that's basically nothing but the ending balance for year 4, right? So essentially in year 4, you're paying this, the balloon payment, $34,000 in a little bit, plus you also don't forget that there's another about $7,500 on top of it, right? The interest and principal reduction. So this would be basically the sum of these two. So it's like 42,000 roughly is your last payment during the 4th year. Okay, so going back to this slide, I've just shown you where to find it in our amortization schedule. So it's just the ending balance for that year. But there is a different way. You can also say that, so let's say you don't have the amortization schedule. You don't have it built. How else could you find the balloon payment? The balloon payment basically reflects how much you still owe to your bank, and it also reflects what's still remaining. If you are prepaying the loan after 4 years and the loan is originally for 10, then there are 6 remaining payments, and we need to essentially add them up, but in the correct way, the way we do it in FRL 3000 class in finance. We find their combined present value, right? So we basically discount all of them back to end of year 4 and then add up the 6 individual present values. How do we do this? You can use the formula to find the present value of an ordinary annuity with 6 payments at 8% interest rate, each payment being our total for each year. Or in the financial calculator, you are computing the present value, PV. You're using the PMT payment of almost $7,500. IY is 8%, and the number of payments is 6 remaining payments, compute PV. So these are kind of, all the different ways how you could do it. Look up amortization schedule if you have it in front of you already built, or use the formula to find annuity present value, or let the financial calculator do it for you. And here, let's just do it in the financial calculator. Let's clear everything, start all over again. Payment is $7,451.47. Let's make it negative, and the only reason we make it a negative number is so that when the calculator shows us the answer, it's shown without any negative signs. Okay, so we want to save it as payment, PMT, the repeating annuity amount. We have 6 of those future payments. We press 6N. 8% is the interest rate that we are paying to the lender, 8 IY, and we are computing the present value, $34,447.25. So I guess here it's a little bit rounded. That's why I'm 2 cents off, but it's otherwise done correctly. Okay, so we looked at, the different loan types, and this is the end of chapter 6.